Okay.
Can I start now?
Let's wait a bit, just 2 minutes, and then we're gonna start.
Okay.
Okay. I think we should start now.
Okay.
Cele, are you ready? Can you start?
Yeah, you can start.
Okay. Morning again, learners. Today we are doing Euclidean geometry, as I indicated yesterday. So today we're going to be doing Euclidean geometry for grade 10, 11, and 12. And your grade 10 person is Lindani Cele. Lindani Cele is a former master's student at UKZN. He's now doing his PhD. So he knows a lot about what he's going to talk about. Just to remind you that at 12, there's a science show today by Dr. T, I believe, or no, I'm wrong, Dr. Konrad. So there's a nice science show at 12. Please come back for it. It's gonna be nice. Otherwise, for now, let's just do some mathematics. Lindani, over to you.
Okay, thank you very much, Doctor. Good morning, everyone. As Doctor said, I'm Lindani Cele, and today we are doing grade 10 Euclidean geometry. This is very important to understand, since the concepts we'll be talking about today, we're gonna need them. Next day, we are doing grade 11 and grade 12. So let's get into it, okay? Firstly, we'll do some revision from basic grades, okay? So we'll talk about some parallel lines, triangles, and all of that stuff, okay? Then we'll follow about a midpoint theorem. We'll then talk about quadrilateral, and we'll give some example or questions about Euclidean geometry. Okay, let's do some revision. Let's talk about lines and triangles, okay? We have parallel lines. Now, what are parallel lines? By parallel lines, we're talking about two straight lines in a plane that do not intersect each other at any point, okay? So these two lines are parallel, and they always indicate parallel lines using this to show that these two lines are parallel, okay? What you need to know about parallel lines, you need to understand that parallel lines, there's something that is called alternating angles, corresponding angles, and co-interior angles, okay? What are alternating angles, okay? Alternating angles, if we have two parallel lines like this and other line like this, so these two angles here are said to be alternating angles. So this line is parallel to this line, okay? These two angles are alternating angles, okay? What about alternating angles if we have parallel lines, okay? So alternating angles are equal, okay? So if we have alternating angles, we always know that they are equal, okay? Now let's talk about corresponding angles. What are corresponding angles, okay? We get corresponding angles if we have two, okay, and we have an F shape, okay. This line is parallel to this line, okay. Now, the corresponding angles are these angles, this angle and this angle, okay. What about corresponding angles? Corresponding angles are equal to, so this angle is equal to this angle here, okay. Now let's look at the co-interior angles, okay. Co-interior angles, we have two parallel lines again. This line is parallel to this line, and we have a kind of U shape, okay. So this angle and this angle are called co-interior angles, okay. So the co-interior angles add up to 180 degrees. So if we have this angle and this angle, you know that let's say this one is X and this one is Y. So we know that X plus Y is equal to 180 degrees. Okay. So in Euclidean geometry, you know that everything that you are saying, you need to give a reason for it. So the reason here would be co-interior angles. Here, alternating angles and corresponding angles. Okay, let's look at the perpendicular lines. What are perpendicular lines? Perpendicular lines are two lines that meet at right angle. So they meet at a 90 degrees angle. Okay, so if we have a line, this if you have a line and this, and here we have 90 degrees. So we know that this line is perpendicular to this line. Okay. Let's talk about a triangle. What is a triangle? A triangle is simply a closed polygon with three straight lines and three angles. Okay. This is a triangle. And triangle have these special properties. The sum of angles in a triangle add up to 180 degrees. So if we have a triangle like this, and you know that this is X, Y, and Z, we know that X plus Y plus Z is equal to 180 degrees. Again, you need to give a reason. Reason, sum of angles in a triangle. Okay. Again, the exterior angle of a triangle is always equal to the sum of the two opposite interior angles. Okay. Let me show you that's again. We have a triangle, right? And this is the exterior angle in this triangle. So if you want to calculate this angle, let me call it T. If you want to calculate T, we know that T is equal to X plus Y. Again, your reason will be this one, exterior angle of a triangle. You know that exterior angle of the triangle is always equal to the sum of the two opposite interior angles. Okay, let's look at this last property. Angles opposite equal sides are equal. So if we have a triangle like this, and they tell you that this angle, this side is equal to this side, so you know that this angle is also equal to this angle. Your reason is angles opposite equal sides. Let's look at the midpoint theorem. The midpoint theorem states that the line segment in a triangle joining the midpoint of two sides is said to be parallel to the dead side and half of the length of the dead side. What does that mean? If this is equal to this and this is equal to this, so this line is parallel to this line, and this is twice to this. So that means if you have X here, you know that here you have 2X. That's what the midpoint theorem states. Okay. Let's look at the quadrilateral. What is a quadrilateral? Quadrilateral is a closed polygon with 4 sides, 4 angles, and 4 vertices. Okay. In Newton geometry, we normally focus on the special quadrilateral such as square, rectangle, kites, parallelogram, and rhombus. Okay. Now, let's look for example of what we've been talking about. Okay. Let's do question 1. Okay, in the statement they gave you that in a triangle AEB, this AP is parallel to DF. Okay, this is what they use for parallel lines. Calculate with reason the size of all angles indicated with small letters. Okay, so we need to calculate the size of X, Y, and Z. Okay, so we see here, let's calculate X. You see we have a triangle here. We have a triangle FDE. Now we want to calculate X. How can we calculate X from the information that we have been given? Okay, we know that 80 degrees plus 4x is equal to 8x. What is your reason? Exterior angle of a triangle DFE. Okay, so we want to calculate the value of x. Okay, let's just transpose 4x to the right hand side. So it will be 8x minus 4x, right? So which is 80 degrees equal to 4x. Now let's divide by 4 on both sides because we want the value of x. Okay, we divide by 4 here and divide by 4 here. So we have x is equal to 20 degrees because 80 divided by 4 is 20 degrees. Now we have the value of x. Okay, that x is 20 degrees. Let's calculate the value of y. Okay, to calculate the value of y, we see again that we have a triangle. We have a triangle, so we know that 80 degrees plus y plus 4x is equal to 180 degrees. Your reason would be sum of angles in a triangle. Which triangle? Triangle DFE. Okay, so we know the value of x here. So we have 80 degrees plus y plus 4 times 20 degrees, which is equal to 180 degrees. This is 20 degrees because we know the value of x from here, right? Okay, we need to solve the value of y. So it would be 80 degrees plus y plus 4 times 20, which is 80 degrees, is equal to 180 degrees. So y plus 80 is 160 degrees, which is equal to 180 degrees. So when to solve for y, it will be y is equal to 180 degrees and transpose this to the right hand side. It will be minus 160 degrees. So our y is equal to 180 degrees minus 160 degrees, which is 20 degrees. Now we only left with a value of z. Let's calculate the value of z. Okay, so remember, this is f shape, right? You see this f, right? So we've been told, because we've been told that this line is parallel to this one. So if we can draw this F here, we know that we have corresponding angles. So this angle is equal to this angle. So Z is equal to 80 degrees. Why? Corresponding angles. Okay. Let me erase this. Now we're done with number one. Let's go to number 1.2. Okay. ABDC is a trapezium with AB parallel to DC. Okay, and DA is equal to DC and BA is equal to BD. The angle ABC, this angle ADC is equal to 20 degrees. Is equal to 20 degrees. Determine the unknown angles with reasons. So we need to find angle X, angle Z, and angle Y. Okay, but it's so that this is equal to this. Remember that angles opposite equal sides are equal. Okay, so what does that mean? This means here is equal to X. So angle C is equal to X. Why? Angles opposites equal sides. Okay, they told us that this side AD is equal to DC. So we have X here, and we want to solve the value of X. Okay, again, this is a triangle. Let's say this triangle here. We have a triangle here. So since we have a triangle, we know that sum of angles in a triangle add up to 180 degrees. So X plus 20 degrees is equal to 180 degrees. What is your reason? Sum of angles in a triangle ADC. Okay. Now X plus X is equal to 2X. Plus 20 degrees is equal to 180 degrees. Now, 2x is equal to 180 degrees minus 20 degrees. I just transpose this to the right-hand side and it's become negative. So we have 2x is equal to 180 degrees minus 20 degrees equal to 260 degrees. So let's divide by 2 on both sides so that we left with the value of x. So our x is equal to 160 degrees divided by 2, which is 18 degrees. Which is 18 degrees. So we have solved the value of x. Let's solve the value of y. You want to solve this y, okay? Again, AB is parallel to DC. So this one is parallel to this one, okay? Let me draw this for you. What does that mean? That means this angle is equal to this angle. So Here we have 20 degrees. We can write it that angle D A B is equal to 20 degrees. Your reason, alternating angles, since AB is parallel to DC. So you will know that we have 20 degrees here. But they tell you that this side is equal to this side. And we know that angles opposite equal sides are equal. So that means our y is equal to 20 degrees. So reason angles opposite equals this side is equal to this one. Okay, lastly, let's calculate the value of z. We know that we have a triangle. This triangle here. Once we calculate this angle, we have this one and this one. We know that sum of angles in the triangle add up to 180 degrees. So z plus 20 degrees, because we have 20 here, plus 20 degrees because we have 20 again here, is equal to 180 degrees. Your reason, sum of angles in a triangle. Okay, so you have z plus 40 degrees is equal to 118 degrees. So z is equal to 180 degrees minus 40 degrees. I just transpose 40 to the right hand side, which means our z is equal to 140 degrees. Okay. Now let's go to number 1.3. In a sketch below, KPMN is a parallelogram. Okay, we have a parallelogram. We have a parallelogram, and they say that ON bisects KNM. So this one is equal to this, and OM bisects NMP. Again, this and this are equal. So let's say let N2 be equal to X. We have X here, and M2 be equal to Y. Okay, so they told that ON bisects KNM. So we have X here again, and here we have Y, because OM bisects NMP. Right. So they want us to show that MOM, NOM, this is equal to 90 degrees. Okay. So let's calculate this angle. We have X here and Y here. So we know that, let me call it O2. O2 plus X plus Y is equal to 180 degrees. Why? Sum of angles in a triangle ONM, right? So we have that our O2 is equal to 180 degrees minus X minus y, which is equal to 180 degrees minus x plus 1. Okay, I just factorize here, put minus outside, and we have x plus y. Okay, we know that this plus this are equal to 1. This plus this are equal to 180 degrees. Why? Because they are co-interior angles. You know that if you have two parallel lines, the co-interior angles are equal to 180 degrees. So we have x plus x, which is this, right? Let me put in bracket this angle, plus this angle, which is y plus y, is equal to 180 degrees. You're using co-interior angles, okay? So we have 2x, right, plus 2y. This is equal to 180 degrees. Let's factorize. Take out 2, we left with x plus y, right, is equal to 180 degrees, okay? Which means if we divide on both sides by 2, we divide by 2 to cancel this 2, we're left with x plus y is equal to 180 degrees minus, 180 degrees divided by 2, which is 90 degrees, right? So we have the value of x plus 1, that is equal to 90 degrees. Now let's go back to O2, which one to calculate. 180 degrees minus, we know that x plus 1 is 90 degrees. So put 90 degrees here, which means our O2 is equal to 90 degrees. So we're done proving that NOM is equal to 90 degrees. Okay. Question 2. ABCD is a parallelogram. Okay. You need to know the properties of the special quadrilateral, such as parallelogram, rectangle, kite. So if they tell you that this is a parallelogram, what you need to think, this and this are parallel, this and these are parallelogram. Why? Because it is a parallelogram, right? So since these are parallel, and we see that we have a Z shape. So this is equal to this. So x is equal to 44 degrees. What is your reason? Alternating angles, AB is parallel to DC. Okay, so we have 44 degrees here. Okay, let's calculate y. This is y. We have been told that this and this are equal. Okay, so angles opposite equal sides in the triangle are always equal. So what you know that is y is equal to x. So your reason, angles opposite equal sides. Okay, angles opposite equal sides are always equal in a triangle. So our y is equal to 44 degrees. So we have 44 degrees. Okay, as I told you that you need to know the properties of the special quadrilateral. Okay, since this is a parallelogram and we need to calculate angle Z. This angle B, which is the right. So we know that in a parallelogram, so y is equal to which is equal to 44 degrees, because we know the value of y. Reason opposite angles in a parallelogram. Okay, so opposite angles in a parallelogram are equal. Now we're done with question 2. Let's go to question number 3. Which is a question that need you to know the properties of the midpoint. This one is 25.4 divided by 2. Okay. Now we have that this is parallel to this. We want to solve the values of x, y, and z. Let me draw this for you. You see this F shape here. What does that mean? That means this angle is equal to this angle. So what we know for now is that x is equal to y. Reason corresponding angles. So corresponding angles are always equal because DE is parallel to AB. Okay. Now, on the other side, we have the triangle. We have a triangle ABC, and we have this angle and this angle. We only have one unknown angle. So 90 degrees plus y plus 32 degrees is equal to 180 degrees. Okay, so our y plus 32 degrees is equal to, I'm transposing 90 degrees to the right hand side, so it would be 180 degrees minus 90 degrees. So y plus 32 degrees is equal to 90 degrees. But we're solving for y. So our y is equal to 90 degrees minus 58 degrees. So we've just solved the value of y. Sorry to cancel this. Okay. Okay, thank you. Okay. Now we want to solve for z. We want to solve for z. So we know that since this is twice to this, so z is equal to 25.4 centimeter divided by 2. Your reason it would be midpoint theorem. Okay, so midpoint theorem state that. So this z is equal to 13.4 0.2 centimeters. Okay. We just solve the value of x, y, and z. Let's go to question 4. Triangle PQR is an isosceles triangle with QR equal to 20 degrees, so 20 meters, and QPR angle is equal to 105 degrees, which is this angle here. Okay, so this line is equal to 20 meters. So they say determine the length of PQ. This is our PQ that we need to determine. PQ. So and they gave us the hint that contracts the height of triangle PQR. So before we do that, okay, we know that this is equal to this, which means this angle here is equal to this angle here, right? Let's call this angle X. So what does that mean? That means we have X here, okay? So let's calculate the value of X first. 105 degrees plus X is equal to 180 degrees. Reason sum of angles in a triangle. The triangle PQR. Okay, so we have 105 degrees plus 2x is equal to 180 degrees. Okay, now we want to calculate the value of x. Let's transpose 105 degrees. So it should be 2x is equal to 180 degrees minus 105 degrees. So 2x is equal to 180 degrees minus 105 degrees, which is 75 degrees. Okay. Now divide by 2 on both sides. This and this cancels out, which means we have x equal to 75 divided by 2. And 5 divided by 2, which is 37.5 degrees. Okay, so we have the value of this, and that it is equal to 37.5 degrees. Okay. But they gave us the hint that so we need to construct the height of the triangle. Okay, let's construct the height of this triangle. We have 90 degrees here. Okay. Now, let me take you to trigonometry. Okay, we know that in trigonometry, cos of theta is equal to adjacent over hypotenuse. Okay, hypotenuse is the longest side. Again, sine theta is equal to opposite over hypotenuse. hypotenuse, right? So here we need to solve this side, okay? And since we just constructed our height here, we have that this was 20 degrees, right? So this one and this one are now equal, which means we have 10 meters here and 10 meters, okay? So what we have adjacent side, which is this one, adjacent to this angle. This is our angle data, okay, which we just calculated that it is 37.5 degrees. So cos of 37.5 degrees is equal to 10 meters, which is this side, adjacent side, over hypotenuse side, which is the side that we're looking for, which is PQ. PQ. Okay. Want to solve for PQ, let's multiply by PQ on both sides. So we multiply by PQ here and PQ here. This and this cancels out, and we're left with PQ times cos of 37.5 is equal to 10. So our PQ is equal to 10 over cos of 37.5. Okay, so you'll get your answer of this side PQ. Let me erase this. So the key point in this question is to understand that in an isosceles triangle we have this side is equal to this side as they indicated, though that means this one is equal to this, and calculate this angle, obviously, which is equal to this one, but we only need this one because we want this side. And they told us that we need to contract the heights. So if we contract the height 12, we'll have 90 degrees here, okay, which is obviously equal to this angle is 90 degrees too. And this one are equal after contracting this. So we have 10 here and 10 here, so you are done. Okay, we're done, guys, for today. Thank you very much for attending. Can you hear me?
Sorry, Lindani.
Okay, okay.
Yeah. Let me just see whether we have questions here. I don't see any questions in the chat box. Do we have questions? If you have a question, you can just raise your hand and Snare will mute you. Don't see any hands. Okay. Thanks, Lindani, for the lesson. Please, learners, please remember that at 12 you have to come back for the science show hosted by Dr. Konrad. So there's that. Please do come back at 12. For now, we're just going to have a session with grade 11s under the same topic of Euclidean geometry. If you want to stay for the grade 11 lesson, it's fine. You're welcome to do so. But if you want to stretch your legs and then come back at 12, that is also fine. Thank you. Chevarra, I see you are there.
Yes, good morning.
How are you?
Good.
I'm good. Please try and share your screen.
Okay. Is the background looking okay?
It's fine.
Okay. Okay.
Yeah. Okay, let's just wait for it to come up.
Has it shown?
Yeah, it hasn't. Not there yet.
Okay. Let me just maybe do it again. Yeah, my connection seems fine. So can you see that for now before I put it on full screen?
Yeah, I see that.
Okay, let's see. Let me say play slideshow. Now?
Not coming up yet.
Is it just a blank screen then? Or?
It is a blank screen.
Oh, that's interesting.
Chevarra, can you see it?
No. I'm only seeing the cursor, the mouse cursor.
Yes. That's what I see as well.
Okay, maybe I can maybe put it into a PDF and then share it. It'll take me just 2 seconds.
Yeah, for sure. I was about to suggest if possible.
Yeah.
You can do that. Okay.
Yeah, sorry, I don't know why it's doing that.
Yeah, I have no idea.
Okay. Okay, let's try this again. Okay, is that better?
Yes, we can see it now.
Okay, good. Okay, so I'm glad that works. I was getting a bit worried.
Yeah, that's perfect.
That's fine now.
Okay, cool.
Let's just wait for 5 more minutes,
No,
Chevarra,
sure.
because the grade 11 will join at
No
that time.
problem.
Yeah.
I'll see you back in 5 minutes.
Okay. Yeah, I think we should start now. They will join us along the way, Chevarra. Good morning, grade 11s. Today, as mentioned yesterday, today we are doing Euclidean geometry, and we have an excellent teacher for that. That is Chevarra Hansraj. Chevarra is a postdoctoral fellow at UKZN. Chevarra, over to you.
Thank you, Simo. I'm just going to share my screen if you can just do the check with me. Okay, can you see that?
Yes.
All right.
Perfect.
Thank you. Well, good morning, everyone. I am Dr. Chevarra Hansraj, and I'm an astrophysicist in UKZN. I firstly want to thank the organizers for giving me the opportunity to share my love for mathematics with the young minds of today. After all, it's you guys that are the future. You're going to build the future. And a special thanks to Dr. Simo Mtetwa. This is a great initiative, and keep up all the fine work that you're doing for young people learning mathematics. So as my opening slide says there, today we're going to be talking about Euclidean geometry. So I know, you're not so sold on geometry. It may not be your favorite thing. Perhaps you may find it a little bit boring. You may think, oh, it's basically all just theorems. First, we've got to prove those theorems, and then we've got to use those theorems to then prove other things. So like, where's the fun in that? But geometry is actually a very interesting study, as I think I've cultivated a deep love for it over the years. So firstly, we should discuss then what is geometry. So if you go on Wikipedia, this is the definition that kind of comes up there. This is the standard definition, I guess. So it says that it is a branch of mathematics concerned with properties of space. So properties of space that can be like distance, shape, size, angles, points, dimensions, area, volume, the relative positions. So that's quite an extensive study, and it basically all relates to structure. And Euclidean geometry really deals with flat shapes. So again, they're probably not the most interesting shapes, but I suppose a common question that we get asked as mathematicians or in the study of mathematics is, how do we apply our field of study in everyday life? What are the practical applications of what we're working on? Well, I suppose, if you really think about it, we do come across many flat shapes. We do see some circles, some triangles, some squares, some quadrilaterals around. So yeah, I guess that is true. We do see it in daily life. But did you know, though, that geometry is present in every facet of life? It just may not be as evident. So how about the question on that slide there? It says, what do the following items have in common? So basically we have the Mona Lisa there. So what do the Mona Lisa, the rose, and the human arm have in common? I'll give you like 5 seconds to think about it. Probably could be, oh, I have a hand that's raised.
Hello, ma'am. Is it the golden ratio?
Hi. Yes, very good, very good. That's exactly right. It is the golden ratio. And imagine, you've been learning about Euclidean geometry so much. Perhaps you have come across the golden ratio, but we mainly use Euclidean geometry to use to have its applications in like circle geometry and triangle geometry. But yes, very right, Kyun. That is the golden ratio. And basically how it works is that if you consider a string and you cut it once, so you have like a larger piece and you have a shorter piece, then basically it's the ratio of the whole string to the larger portion is the same as the ratio of the larger portion to the smaller portion of the string. So if you look at basically, it was also developed by Euclid, like I mentioned earlier. So I think that, we can agree that he was a pretty cool guy, because that's pretty cool, linking all of these things together. But so if we look at, I'm just trying to move the Zoom participant thing so I can see the ratio of the arm. Here we go. Yeah. So if you're basically looking at the average human arm there, so you have like the longer piece here, right, and the shorter piece here. So basically in an average human body, the ratio of the whole arm to the forearm is the same as the ratio of the forearm to the hand part, the smaller part. And interestingly, this proportion is also present in the Mona Lisa. So if you look at the Mona Lisa over here, basically the ratio of the width of her forehead is in proportion to the length from the top of her forehead to her chin. So that's what you call the golden rectangle. It's basically the same thing as the golden proportion, just in rectangular form. And then in the middle here, this kind of proportion is also present in the rose. This is what you call like a Fibonacci spiral, but it is also kind of displaying the golden proportion or the golden ratio at work. So perhaps, it does kind of beg the question then, is this why the Mona Lisa is so aesthetically pleasing? Is it because of this proportionality that we are all so fascinated by it? I have seen the Mona Lisa in person, and just aside this thing, we visited the museum, the Louvre Museum, and when we got into the hall, there were thousands of people. Well, not thousands, okay, that's an overstatement, but the room was packed, and it's just like probably the size of maybe your school hall, and there was just you couldn't actually see it because it was that tiny. But yeah, this golden proportion is so. I wish I could see it like literally up close, so I could really like maybe even do a measurement type thing. But trust me, it is in proportion. Okay, so yeah, so we have geometry that could be hiding in plain sight. And speaking personally about my journey with geometry, it's been kind of an interesting one. So of course, in school, they make us do all of these projects, right? And I always, subconsciously gravitated towards the ones that involve geometry. They used to give us like choices. And so, yeah, that's the one that I would write about. So in grade 11, we were given, I did a project on taxi cab geometry, which is basically the Manhattan distance. And then in grade 12, I did the golden proportion. I put the years there, which I think is kind of giving away my age, but yeah, anyways, I did the golden proportion, and it was really cool seeing how many, literally in how many areas you can apply the golden proportion to. It's in art, it's in fruit, it's in architecture. Obviously, would be in architecture. That's maybe not surprising, but it's in nature, in like a butterfly's wing, in the way the patterns on pineapples, the way those are arranged, and the number of little like oblong shapes there. Those are all using the golden ratio. So yeah, who knew that certain things like these, like the Mona Lisa, the rose, and the human forearm could be related? But yeah, through magic, math. So yeah, cutting to today though, after all of those years, studying geometry in school, and of course, when you get to university, and if you take math, of course, you're going to do some more different kinds of geometry, some more analytical geometry, some manifold geometry, and so on and so forth. But yeah, today, basically, cut to today, the subject of my PhD thesis was basically about the geometry of the rotating black hole. So I basically investigated theoretically the geometry around the rotating black hole and all its properties, like what happens when you get close to the black hole, how does the space-time change or warp? That's basically geometry, how space changes, right? So what happens to properties of acceleration, expansion, distortion, and even twisting. So we have to start. Putting that all into perspective, I had to start somewhere. And so, in these kind of studies, we've got to start somewhere, and we have to start with triangle and circle geometry and quadrilateral geometry before we get to the more exciting things like black holes and stuff like that. So coming back to Euclidean geometry. So of course, like we mentioned earlier, we're going to be, going through some proofs. So that's happening. And it's based on, Euclidean geometry is basically based on axioms and theorems. And we're going to look over their proofs as well as, I'm just going to be stating their converses. And basically how I like to view the section in Euclidean geometry is it's like a game. Okay, and you've got basically these are the weapons that you have. I drew them as like arrows, right? Like you have some arrows, you have some arrows in the back there, and you've got a bow, and you've basically got to like load up your arrow and shoot it at the target, which is basically how to prove what they're asking you to prove. Right, so you've got the selection of quiver of arrows, and then you need to fire basically at the target. And the arrows are going to be your theorems and your axioms that we need to study and we need to use to prove what this question is, so that we can hit that bullseye. And that it means we answer the question and we also get the marks in the exam. Yes. Okay. So what kind of weapons are we going to be using today? So we've got firstly the theorem of Pythagoras, right? Then we've got angle at the center of circle. Okay, so that's another weapon. There'll be theorems that are associated with them that we're going to look over. Then what about cyclic quadrilaterals? Cyclic quads. That's our third weapon. And our fourth weapon that we're going to be considering today is the tangent to the circle. So I think all in all, there are about like 9-ish theorems. They also have converses, corollaries, and so on and so forth. It's hard to get through all of them, obviously, in our session together, but I'm going to try my best to review a lot of them. And then, of course, put them into practice because, of course, the examples are what matters the most. Okay, so let's get started with the theorem of Pythagoras. So again, we don't have to spend too much time with this. I'm sure you've been using it quite a bit, but basically in a right-angled triangle ABC, the square of the hypotenuse side c squared, which is this here, c squared is equal to the sum of squares of the other two sides, a squared and b squared. So this is a and b, you square them and you get c squared, right? This is for a right angle triangle. Okay, sorry, just something popped up on my screen. Here we go. All right. Okay, and then we have, so that was our first theorem, right? The theorem of Pythagoras. And then we have theorem 2, which says that the line drawn from the center of a circle. So if we have a center of a circle O here, and we have these chords AB, right? And C is here on AB, such that it makes OC and AB perpendicular to each other. So this is our setup. So it says that the line drawn from the center of the circle perpendicular to a chord bisects the chord, meaning that it cuts it in half, meaning that AC is equal to CB. Okay, so if we have to prove this theorem, that's what it's asking us to prove, right? AC is equal to CB. That means that this chord is cut in two, or it means that it bisects it, meaning it's cut into two equal portions, right? So that's what we're required to prove here. I hope you can see my cursor. This is what you're required to prove here. And then you can do a construction, right? You can join OA and then OB, right? So it's done here in dashed lines. And then the proof goes as follows. So basically we have two triangles here, right? We've got AOC and we've got triangle BOC, okay? And so those are the two triangles there. We know we've got a right angle somewhere there. So then if we had to prove this, so now obviously we want to prove congruency, right? So we've got AO here, and we know that it's going to be AO and OB are going to be equal to each other because they are radii, right? So this is the O here represents the center. So OA and OB, which A touches the circumference, B touches the circumference. So this is the radius. OA and OB are going to be the same, so they're equal. Then we also got that the angle OCA and the angle OCB, meaning this angle here, and of course on the left-hand side of that, is going to be 90 degrees. You can do angle in a straight line, or which means that if this is 90, then this has got to be 90. But anyways, we have that OC and AB are perpendicular, so we would expect that. And then we have that OC is common, right? This is common to both triangles. This side is in this triangle and this side is in this triangle, so it's common. And so we can prove that AOC is congruent to BOC. So that's with 90 degrees hypotenuse side. That's quite a simple proof. And because of that, we can then say that AC and CB are going to be like AC, and CB are going to be the same. Okay, so that's basically how you do that that proof. So we're going to be using this. The main thing, I guess, is to remember that we're using this this theorem, right? The line drawn from the center of a circle perpendicular to a chord bisects the chord. Okay, and then there's also a converse, right? So if you have, the converse is like basically reading the theorem that you just proved back to front. So it's kind of like starting at the end and finding the beginning. So the converse then would state that the line drawn from the center of a circle to the midpoint of a chord is perpendicular to the chord. Okay, so remember we were given in the previous slide that OC and AB were perpendicular. Now we've got to prove that they're perpendicular. And so we do that by joining again OA and OB. And then looking at the triangles again, we've got OA and OB being radii. So we've got that again. We also have the line is drawn from the center of a circle to a midpoint of a chord. So we have that AC and CB are the same, right? And that's also in our given information here. And then we've got OC common. So we've got radii, and then another side, and then a common. So we've got side, side, side. And so that means that we have that OCA is equal, angle OCA is equal to angle OCB, meaning that this is 90 degrees and this is 90 degrees, which basically tells us that OC is perpendicular to AB, right? Otherwise, this would not be, these would not be 90-degree angles. All right, so moving along. All right, so we basically tackled one weapon that we have. We've loaded it into our I didn't actually look up what the carrying pouch is called for the arrows, but we've got it locked and loaded there. And now we're going to investigate our next tool, and that's going to be the angle at the center of a circle. So we're given that there's a circle O with chord AB. So we've got chord AB subtending angle C. So got that on the circumference and angle AOB at the center, right? So AOB, these are the angles at the center. All right, so the theorem then states that the angle a chord subtends at the center of a circle is double the angle it subtends at the circumference. Okay, so the angle a chord subtends at the center of the circle, meaning this, right, is double the angle it subtends at the circumference. So this angle here is double that angle there. All right. So, of course, this angle at the center of a circle theorem can be proved in many ways, or rather there are many different setups or scenarios, but this is just one of them, and we'll mention the other, I think there's 3 afterwards, but we're just proving this one for now. Okay, so we're required to prove that the angle AOB, which is this angle here, is twice angle ACB, which is this angle here. So the construction is to draw CO past O to this point D here. And then what we do is we let this angle C1 be X. Okay, so this is X. And we let angle C2 be Y. All right. Now, we know here we have this similar setup as the previous question. We have OA and OB, and we also have OC being radii, right? Because O is the center. Right, and if we draw a line coming out of the center and touching the circumference, that is a radius. So we have that this angle A here is going to be the same as angle C1. Why? Because OC is equal to OA. They're both radii, right? So it's kind of like you've got an isosceles triangle here. And so we've got that this is going to be equal to X. And in a similar way here, you've got OC and OB. They're both radii. And again, you have an isosceles triangle here. And so this will be Y. Okay. I think I put it there. Yeah, there we go. So now you can see it more clearly. So you've got your X's here, and these are your Y's. Those are your angles. All right. So we've gone up to here. So now if we look at O1, okay, it's going to be equal to 2x, y. So O1 here is going to be equal to 2x, y, because it's the exterior angle of the triangle CAO, right? So your exterior angle is going to be equal to the sum of the interior ones, opposite ones. So x and x, so that's going to be 2x, right? And then you have O2, and a similar thing is going to happen. You've got y and y here. So you've got an exterior angle of a triangle, COB or CBO. And so this is going to be 2y. So if we put that on the diagram, that's what we have. Okay, so then if we had to find out this entire angle, remember we wanted to find out what the angle was for AOB. So this includes O1 and O2, right? That becomes AOB. So angle AOB is going to be 2x plus 2y, and well, you can take a common 2 out of there. It'll be 2 into x plus y, and we know from earlier that we labeled C1x and C2y. So the whole angle C is C1 and C2, which is x plus y. So we really here proved that angle AOB is equal to twice angle ACB. And that is basically proving the theorem that the angle a chord subtends at the center of a circle is double the angle it subtends at the circumference. Okay, so there are other cases where you can see this exact theorem, right? So this is the one that we, I think, just focused on, but you can also have it in this way. So you see, you've got the angle at the center, and now you've got kind of a subtending like this. So it's not like in front anymore. It's kind of like to the side. So this angle is still 2 and 2 times x, and this one would be x. Here you have a similar thing. It'll be an angle like kind of like this way, like an upside down type of thing. This would be 2x this way, and that would be x. A good thing to note here is that the converse is not necessarily true. So this one at least doesn't have a converse. All right, and then we have another theorem. The angle subtended at the circle by a diameter is a right angle. Or basically it's the theorem that's called the angle in a semicircle, which is going to be a right angle. So the proof basically follows from the theorem that we proved before, right? We said that from before that the angle a chord subtends at the center of a circle is double the angle it subtends at the circumference. So when the angle at the center, which is, so this is the center, right? If, well, somewhere here, if the angle at the center is going to be 180 degrees, right? That's going to be 2 times x, which is what is opposite here. So our x here is going to be 90 degrees, right? Half of 180 degrees. And so in the sketch, we have that C is, angle C is 90 degrees when AB is the diameter. Okay, so that's a nice, quick, simple proof. So basically, we're going to call this angle in a semicircle just for later purposes when we have to prove that. And its converse is if the angle subtended by a chord at a point on the circle is, oh, I forgot to write here 90 degrees. So if it is a right angle, then the chord is a diameter. Okay, so we have come to an end of yet another one of our weapons. So we've got it locked and loaded in the back. And now we're moving on to cyclic quadrilateral. So this is our next weapon that we're going to tackle. So what is a cyclic quadrilateral? It's really tough to pronounce sometimes. It's a 4-sided figure where all 4 vertices lie on a circle. So these are some configurations. You can see that the corners of each of these shapes all lie on the circle. So that's basically the prerequisite for being a cyclic quad. Okay, and we say that these vertices are concyclic, and they have these cyclic quadrilaterals have 3 main properties, and they're going to be expressed in the theorems that we're going to consider. Okay, so we've got this theorem here, the opposite angles of cyclic quadrilaterals are supplementary, meaning they add up to 180 degrees. So basically, if you wanted to do the proof, you want to show that in the cyclic quad that we have there, your A, B, C, D, that angle A plus C are 180 degrees, and angle B and D are going to be 180 degrees. So using our angle at the center of the circle, remember we said that the angle at the center of the circle, so if we take O1, right, which is on this side, that here, this angle here is going to be twice angle C, which is over here. Okay, so that's going to be twice angle C, which is over here. And then O2 here is going to be, remember from our configuration that we discussed in the previous slide, is going to be 2 times the angle at A, because it's angle at the center of the circle. So we've got angle O1 is 2 angle C, and angle O2 is 2 angle A. But we know that basically the angle around a point is going to be 360 degrees, a revolution. So O1 and O2 have to be equal to 360 degrees. That means that 2 times A plus 2 times C is going to equal to 360 degrees. And so if you divide through by 2 all the way, you get that angle A plus angle C is 180 degrees. And then since the angles of any quad are going to add up to 360 degrees, right? So you've got that A and C add up to 180 degrees. The angles or the sum of angles in a quad are going to be 360 degrees, meaning that B and D are going to make up the rest of the 180 degrees. All right, and there you have your proof. Done. Right, and then the converse of that is that if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is a cyclic quadrilateral. So if you have something that you have a quad like looking like this, so if you have D, the angle at D being X, and you find that the angle at B is 180 degrees minus X, then this becomes a cyclic quadrilateral. That's how you prove that. Okay, I think we're going to be using this kind of proof later. So yeah, so moving along, theorem 6 is the exterior angle of a cyclic quad equals the interior opposite angle. Okay, so the exterior angle of a cyclic quad is going to be represented by angle C1 here. And so we want to show that this exterior angle C1 is equal to angle A. Well, the proof is quite simple. Basically, we're given that it's a cyclic quad, A, B, C, D, right? We're given that. So we know that angles A and C2 are going to be equal to 180 degrees, right? Because they're supplementary from the theorem we just did previously. Or you can say, yeah, it's called opposite angles of a cyclic quad. But angle C1 and C2 are also 180 degrees, right? Because this is a straight line. So if you had to add C1 and C2 together, they would be 180 degrees also. And so if you put these two on top of each other, you'll see that angle A and angle C1 will be equal to each other, right? If you kind of do a process of elimination or you make C2 the subject of the formula, you will see that angle A is equal to angle C1. So we've got that the exterior angle of a cyclic quad equals the interior opposite angle. And then the converse is also true. If an exterior angle of a quad is equal to the interior opposite angle, the quad must be cyclic. All right, so that's how it looks diagrammatically. Cool. Then in theorem 7, the angles in the same segment of a circle subtended by the same chord are equal. Okay, so basically, if you have this chord AB, right, subtending angles C and D at 2 other points on the same segment of the circle, basically, if you kind of imagine that there was a chord here, A and B, right? If you take like a line here and you see that this subtends angle C, and it would also subtend angle D. Okay, and then if you use angle at the center of a circle, you will see that angle AOB is angle AOB is twice angle D, and angle AOB is also twice angle C, which means that angle C and angle D have to be equal to each other. Okay, the converse also applies. If a line segment AB subtends equal angles at 2 points C and D on the same side of AB, then ABCD is cyclic. So there is a converse to that. All right. So before we move on to tangents, I didn't know if I was going to be able to get through everything. So I thought that we'd do something quickly together, an example, because these are what matters the most. So you have 2 circles that intersect at A and B, okay? O is the center of the smaller circle. So we've got a circle here. We know the center is O here, and it lies on the larger circle. And then we have that AOC and OEF are straight lines. So The question is, if angle AFE is x, write down with reasons 3 other angles each equal to x. Okay, so we've got that AFE is equal to x, so it's this part here. How would we go about answering this question? So this question is I guess not difficult, but it's like, it's not asking you prove exactly this. It's saying you write down other angles that equal to x, 3 of them. So you have to start asking yourself questions like, does AFE, subtend something? Is it an exterior angle of something? You know the theorems, right? So it's kind of like working backwards. One thing that we do know is we know that there's a center of a circle, of the smaller circle, which is O. So we know that OA and OB are equal to each other because they are radii of the circle. But these are equal chords of the larger circle also, right? Because these are equivalent because we know that it is radii of the smaller circle. And then they will also be equivalent chords of the larger circle, meaning they have the same length, right? So that means that they are equal chords, and so that they're going to subtend equal angles. So this chord is going to subtend this angle X, and this chord, which is the same kind of chord, is going to subtend this angle F1, and that is also going to be X. So equal chords, equal angles. So we've got 1. Now we know that chord OB subtends equal angles. So we've got chord OB subtends equal angles at A and F, meaning that, so we've got this common chord here. It subtends this angle F, and it also subtends this angle A, right? Can you see that? It subtends A and it subtends F. So we get that angle F1, I think that's what that was labeled, yes, is equal to angle A1 over here. So we've got our second one. All right, what about a third? Well, again, we know that OA and OB are equal to each other. So we basically have an isosceles triangle, and we just proved that A1 is equal to X, right? So we've got this angle here, meaning that because this is an isosceles triangle, this is going to be, which is B2, angle B2 is going to be equal to angle A1, and that's going to be equal to X, right? So we found our 3 other angles which equal to X. Well done. I hope you guys follow that one. So now our second question is, write down giving reasons the size of angle OBC in terms of X. Okay, so we have to write it in terms of X. So we know that we need to keep in mind also what has been labeled X. So we know A1 is X. We know that B3 is X, no, B2 is X rather. We know that this is X, and also F1 is X. So keep that in mind. Anyway, AC is the diameter of the circle, right? So we've got AC being the diameter in red there. So the angle that it's going to stand at the circumference is going to be a right angle in a semicircle. So this is going to be 90 degrees. So if we had to take angle OBC, right, and angle B2, right, so OBC, which is here, and angle B2, which is here, basically we're adding this B1 and B2 together, right? That's going to be 90 degrees. That's going to give you your 90 degrees. Now we already found out that B2 is equal to X, right, from the previous question. We found out that B2 here is equal to X. So if this is X and this whole angle is 90 degrees, then this part here, which is the remainder, is basically going to be 90 degrees minus X. So that's how you get angle OBC. And yes, it is written in terms of X. Okay, a third question. If angle AOE, so AOE, which is here, right? If angle AOE is 2y, what is angle ABE? So what is this angle here? Why? Well, what is it and why? Well, the question is asking why is it equal to y? So it's telling you what it is rather, but you have to find out why. So we have chord AE here, right? It's touching 2 points of the circle, and it subtends angle AOE, which is this angle here, right? And that's going to be 2y at the center, and hence it's going to subtend y at the circumference, right? Because you've got this being 3, and then this being O3, and then it's going to subtend this here also. Okay, so it's kind of like a similar thing as before. You've got this subtending this, and then this AE chord subtending this angle here. So these are going to be, it subtends y at the circumference. So your angle ABE is going to be y, half of that, So the angle at the center, then the theorem that we're using is 2 times the angle at the circumference, right? This is the angle at the center. There's O here, and this is the angle at the circumference. So that's what we have. All right. So that's why angle AOE is 2y and angle ABE is y. Okay. Now it says if AOE is 2y, which we figured that out, prove that EB bisects triangle ABD. So if we locate EB, that's over here, right? EB or BE rather, and prove that it bisects angle ABD. So ABD is this angle here. So we want to find out that it divides this into 2 pieces, basically. This is 2 pieces. So we've got that angle ABF is going to be equal to, which is ABF is going to be equal to angle AOF, right? Because it subtends the same chord. So AF is the chord. It subtends angle, this angle B3 and 4 here, and angle O3 there, right? So angle ABF is equal to angle AOF, which is 2y, right? We have that. But angle ABF here, which is here, is angle B3 and B4, right? It's both of them together. Now we already proved that angle ABE, which is this one here, ABE, or rather B3, is going to be y, right? We just proved that in the previous question. So then angle ABF is, which we just replaced this angle B3 with y. So we've got it's y plus angle B4. Right. And we worked out that angle ABF is 2y. So we can even put that in and make B4 the subject of the formula. So we've got B4 is 2y, right? 2y is ABF minus y, and that is equal to y. And so we have proved then that B3 and B4 are both y. And that means that this BE here bisects angle ABD, meaning that you've proven that B3 and B4 are the same angle. So they're bisected, or rather cut into equal parts. Okay. So we come to, so that was application. We come to our last kind of application, and that's tangent to a circle. So, a tangent is a straight line touching the circle at only one point, basically. And at the point of contact of a radius and tangent, they're going to be perpendicular to each other. Okay, so I'm not going to get too much into the proofs of these. We're basically going to try and apply them mainly. So 2 tangents from the same external point are equal in length, meaning that if you have this external point P here, and you have these tangents PA and PB, they are going to be equal in length. They're from this, because they're drawn from the same point. And you basically have these 2 triangles that are going to give you a 90 degrees hypotenuse side proof that comes out. So you get that AP and BP are the same. That's also to mention that there's no converse for this, or rather the converse is not necessarily true. All right, theorem 9, which is our last theorem we're going to be considering today before we do our one of our final examples. So the theorem 9 says the angle between a chord and a tangent at the point of contact equals any angle the chord subtends in the alternate segment of the circle. Okay, so basically that means that you have an angle between, so you have this chord AB here, right? And it subtends angle C in the alternate segment, and you have this tangent AD. So the angle between a chord and a tangent, meaning this angle here, right? There's your tangent, and that's your chord. This angle here equals any angle the chord subtends in the alternate segment. So here your chord is, it's going to subtend angle E, and it's going to subtend angle C. So these are also going to be X. If this is X, these are also going to be X. And that can be proved. A very valuable tool. And there's also a converse that proves that it is a tangent to the circle if you have that phenomena happening. Okay, so now we've got all our tools, we're locked and loaded, we're ready to hit the bullseye again and consider our next example. So we have, again, 2 circles that are going to intersect at J and I, okay? And then you have here that LH and LK are tangents, and then KIH and KJG are going to be straight lines, okay? So that's basically the setup. All right, So the first thing that we need to do is we want to prove that GH is parallel to KL. So we've got GH here, and we want to prove it's parallel to KL. So we have to do this in a few steps, right? We've got to show that this is parallel. So what we start off with is we say that angle K1, which is over here. It's normally good to start off with angles that belong to either GH or KL, right? Because that's what we're trying to prove. So if we look at KL, we take this angle K1 here, and what we notice is we have a tangent here, right? We said tangent is KL, and then we have this chord KI. So we know that the angle between the tangent and chord is going to be the same as any angle this chord subtends. So we know that angle K1 is going to be equal to angle J3 because it subtends from the chord, right? So angle K1 is equal to J3. And then we know that now if we look at J3, we know that we have a cyclic quad here because we've got these points J, G, H, and I that lie on a circle, right? So we can draw a cyclic quad on that. And so then we know that J3 is going to be, well, that's what we're working with. So that's going to be an exterior angle of this quad, right? If you kind of like extend this line, you have that as an exterior angle, and that's going to be equal to the interior opposite angle, which is going to be this angle H, this angle H here, or angle GHK, yeah, over there. So we've got that angle J3 is equal to angle GHI or angle GHK. And so we've got that angle K1, which is this one, is now equal to angle GHK. So we've got this equal to this equal to this. Okay, but if you look at this angle GHK here and angle K1 here, we notice that these are alternate angles, right? We've got this equaling to this, and we've got a line between them. So that then proves that GH is going to be parallel to KL because we've got these alternate angles being the same, right? You have that like Z shape. I don't know if you can see it. It's like GH, HK, KL, the Z shape. So that's how you prove that GH is parallel to KL. The second question is prove JH LK is a cyclic quadrilateral. So basically you have here your angle G here and your angle GKL, which is over here, being 180 degrees because they're co-interior, right? We have that GH and KL are parallel, so we can just use the co-interior. You have this U shape forming here, right? So these two are co-interior, meaning they add up to 180 degrees. But our angle G here is also going to be the same as angle JHL over here. Why? Because we have this tangent chord situation again. We have this tangent over here and a chord here. So the angle between the tangent and the chord is going to subtend this angle here. So angle G is angle JHL. And basically that shows that this is going to be 180 degrees, right? Because if these two make 180 degrees, if these two make 180 degrees, then these two are going to make 180 degrees. So these are opposite angles of a quad and they are supplementary. So we have that JHLK is a cyclic quadrilateral. Okay, so I'm running out of time. So I think I'm going to just skip to some ending slides. Maybe if we if we have more time, I can do another one, but basically I just wanted to end off by giving some tips on answering some of these questions. So my tips are to basically read the question carefully and extract the information first. You could get a bit flustered seeing a really complicated shape in front of you, but trust me, things are not as complicated as they seem. Ask yourself questions. Does this angle subtend anything? Is it an exterior angle? Do we know if lines are parallel, so they could be complementary, co-interior, that kind of supplementary angles in a cyclic quad? Then what you do is you mark the information that you get onto the diagram. Thirdly, do not assume anything baselessly. So if they haven't given you this information and you haven't proved any part of an information, then do not assume that it is true. Okay, and then do not prove the given information. So if you're given something, don't spend time proving it. It's given to you, it's there for your use. Then always write down a reason for your calculation or answer that you should know. I'm sure your teachers have drilled that into you. And you will likely need to use all the given information. So perhaps if you haven't, used some important information, then, you might have maybe made a mistake somewhere. So go through your work again and see. And then if you're asked to prove something, then you need to know that it is true. So you shouldn't be getting something that's contradictory to that, and you shouldn't be trying to prove the contradictory part of it. You're trying to prove. You can use contradiction, proof by contradiction, as a tool, but you're basically proving that something is true. Then if you cannot prove something, then remember that the result that they've asked you to prove, say they asked you to prove that something is a cyclic quadrilateral, but you don't know how to do that. Then when you do the questions after that, you need to remember that that is a cyclic quadrilateral, and you can use the various properties. Just because you can prove it doesn't mean you need to lose marks also in your subsequent questions. So make sure that you're using all the information at your disposal. And yeah. So that's all. And I would like to say all the best for the rest of 2023 to all the students. And I hope that you're able to pick up a few things that I tried to show today. And again, once again, thank you to the organizers. And yeah, thank you.
Thank you. Thank you, Dr. Chevarra, for a beautiful lesson. So if you have a question for Dr. Chevarra, you can raise your hand or type your answer or type your question on the chat box. Hey, Dr. Chevarra, we don't seem to be having any questions. So
okay, I don't mind. I can do another example if the students would like to do another one quickly, because I did prepare another one. That's if it would probably take about 5 minutes.
go all right.
Yeah, okay. Okay, so I've been allotted some more time. Yeah, if we have to go to example 3, basically, this is the configuration that we have, kind of tangents to the circle here, and with the center O, and you've got, sorry, the thing is popping up, yeah, with center O and the points Q and B. And then radius BO is produced, and it's going to cut the circle at A, and then it's going to make PQ produced at P. So that's kind of the setup that we're working with here. So our first question is to prove that RBOQ is a cyclic quadrilateral. Okay, so what do we know? We know that the radius of a circle is perpendicular to a tangent at the point of contact, right? That's a theorem that we have. So OQ, which is over here, is going to be, perpendicular to RQ, right? So you've got this, the radius of a circle, which is OQ here, is perpendicular to a tangent RQ here. And so OQ is perpendicular to RQ. And the same thing on the other side, you've got OB perpendicular to RB. Okay, so there's the right angles there. And hence we have that angle RBO, which is this angle here, and angle RQO, this angle here, is going to be 180 degrees. Okay, but what do we notice here? We've got a quad, right? So these are opposite angles of the quad RBOQ, and they are supplementary, right? This is 90 degrees and this is 90 degrees. So then we have RBOC being a cyclic quad. A second question would be prove that angle Q3 is half of angle O3. So if we had to locate angle Q3, it would be somewhere over here. And basically, we've got, these are radii, right? We've got OQ and OB being radii. So this angle here, angle Q3, is going to be the same as angle B2. So those are the same. And we also have that angle O3, which is over here. It's going to be an exterior angle to this triangle OQB. Right? So we've got this triangle here. This is going to be the exterior angle, which means that it's going to be the sum of Q3 and B2, right? So angle O3 is Q3 and B2. And so then angle O3 is going to be 2 times angle Q3. Why? Because we already proved that Q3 and B2 are the same. So it's 2 times Q3, or you can even say it's 2 times B2. But since the question is relating Q3 and O3, we keep it as Q3. And then if we make Q3 the subject of the formula, we get that it's half angle O3. Okay, so that's how you do it. Basically, we used equal radii and the exterior angle of a triangle to prove that one. Then if Q1 is equal to X, determine with reasons 4 other angles in the figure, which are each equal to X. So if you have angle B2 here, all right, it's going to be equal. So remember, we've got Q1 is equal to X. So this is that. So if we have a tan chord situation again, where PQ is going to serve as the tangent and AQ is the chord. So the angle between the tangent and chord is Q1 there. That's equal to X. And we know that this chord AQ subtends angle B2, right? We've got this B2 here. And so we get that B2 is equal to X also, the same as Q1. So that's one. We've got to find 3 other ones. The second one comes from the fact that OQ and OB are radii, equal radii. So if this Q3 is equal to X, which we have, then this angle B2 is going to be equal to X, or rather the opposite way around. We just proved that angle B2 is X. So this angle Q3 has got to be X as well, right? Because of the fact that this is an isosceles triangle. So we've got a second angle. So now we've got that angle Q1 is X, angle B2 is X, and then angle Q3 is X. We've got to still find 2 more. So another thing that we know is we've got that Q3 is equal to X, and we have, or rather already proved, that RBOQ is a cyclic quadrilateral. And so we've got a situation of angles in the same segment where you have this chord here, this common chord OB, it subtends angle Q3 and it subtends angle RB. Angle R2 rather. So that means that these angles are equal to each other, right? So you've got this chord, it subtends angle Q3 and it subtends angle R2. So R2 and Q3 are the same. And so now we found that R2 is equal to X as well. Okay, and yeah, so in summary, we've got that, we've also have that R2 here is equal to X. Yeah, we did that before. Okay, so in summary, we've got that B2 is X, which is this one, Q3 is X, R2 is X, and R1 is X, which we just did just now. Okay. So yeah, I guess I'll leave it off. I'll leave it off there. If you have any questions, you can ask me. Otherwise, it's been a pleasure to have presented this seminar to you guys.
Thank you. Thank you once again, Dr. Chevarra. So if you have a question, you can ask. If you are too shy to speak on the mic, you can type on the chat box. And I think Dr. Chevarra will also share the beautiful slides that she was doing, she was presenting today. Also, grade 11s, at 12, we have a science show and lucky draws. So if you want to win something, please come back at 12. Or you can stay through the grade 12 lesson that is coming up at 11. So without any further questions, let us thank Dr. Chevarra. Dr. Simo has always said that you are his best teacher. And I can also agree that I really enjoyed your lesson. Thank you.
Thank you. Thank you. Thank you guys for attending and have a good year. Thank you.
Hello, everyone, once again. So now we are about to start grade 12 lesson on Euclidean geometry. And we have Mr. Vezi from Canon College. Mr. Vezi is a very experienced teacher. So he'll take you some of the things that you need to know on Euclidean geometry in order to ace your exams. Mr. Vezi, you can start sharing your screen so that we can, so that we can verify if we see it.
Okay, morning, sir. Let me see. Right, so there's my screen. Do you see anything there?
Yes, we do.
Okay, so yeah. So I think I can start now. It's exactly 11 o'clock. Right. Okay. No.
Yes, please. You can start. Others will find us along the way.
Okay. Thank you, sir. Let's hope the network doesn't disturb us because, yeah, these are hectic times. Anyways, guys, so hello, everyone. So we are just going to go through Euclidean geometry, grade 12 Euclidean geometry. Okay, now obviously, a lot of us actually, well, a lot of people don't really like geometry. I don't know why, because I always say it's probably one of the easiest sections in mathematics, because there's only a few concepts, or you only depend on facts, and there's nothing much that you have to do there, not a lot of manipulation. So let's see what this is about. And then, like I did on Monday, so this is from your examination guideline to say. So it really gives you an outline of what you really need to know as far as geometry is concerned. So in this sense, it gives you the list of theorems which you may be asked to prove, which means this is bookwork. Remember now in your exams, there will generally be one theorem that you have to prove. So these are the theorems which are examinable in that sense. So not all of them are examinable. So there's only 6 of them which are examinable. Then you just have to know them, and then you get all those 5 marks or for whatever the case is, or 6 even. Okay, and then this is just some of the list of basically the theorems and axioms and corollaries that you have from geometry. So please just make sure that you go through these to make sure that you are familiar with all these theorems and everything, particularly the ones from grade 11. Okay, because they play very key roles as far as examination questions are concerned. Okay, so do make sure that you go through this before you write your trials and whatnot. Now, for our lesson, we are mainly going to focus on 2 theorems from grade 12, and they are basically around triangles. Because in grade 11 we focus on circles, in grade 12 we mainly focus on triangles, and then we sort of integrate the 2. Okay, so that's why I was saying circles are very important. Okay, so we are going to look at proportionality theorem, particularly the application of that. But remember that this is examinable, so which means you need to know the bookwork or the proof of this theorem. Also, there's a similarity theorem, which is also examinable, which means you need to know. It's part of that list anyways. Okay, so this is the list of our objectives for today. Now let's start. The first objective was to look at the proportionality theorem. Now it's very important in geometry to understand what the statement is saying, and then you translate the statement to a picture or to a diagram, and then you combine the statement with the diagram, and then you, from that, make sure that every time you use that statement, you then sort of combine or couple it with a reason. Because a reason is just a short way of saying, this is the statement I'm using, because we cannot always be writing this long statement. So we therefore need a reason. So the most important thing in geometry is the statement, to understand what it says. Most important, the important of them all will be the diagram. You need to be familiar with diagrams. And then when you use the statement, you then put a reason next to it. Okay, so let's see what this statement is saying. It says, if you have a line that is drawn parallel to one side of a triangle. So you have a triangle here, A, B, C. And then we are saying that if we draw a line, so in this case, we draw a line DE, but not just any line, the line must be parallel to one of the sides. So in this case, DE is parallel to BC. Obviously, I could have drawn it this way, which will be parallel to AC, or I could have drawn it this way, which will be parallel to AP. It doesn't really matter the orientation. What matters is that the line we are talking about is parallel to one of the sides of a triangle. Okay. So this theorem says, if you have such a line, that line, what does it do? It will then divide the other 2 sides. Obviously, we can see that it divides them. That is obvious. But the theorem says it divides them proportionally. This is the most important part of this theorem. So the line, if it's drawn parallel, it divides the 2 sides. We know that we can see that it's obvious that it will divide the other 2 sides. But what the theorem puts to us is that this line will divide the other 2 sides proportionally. So that is the main word of this theorem. So what does it mean proportionally? So in the same proportion. So the 2 sides are divided in the same proportion or in the same ratio. Remember, a proportion and a ratio, those are identical concepts to say. So now let's interpret, what does that mean? Okay, so the sides which are divided here is side AB and side AC. So what does it mean that they are divided proportionally? Well, it means that if I take a proportion or a ratio on this side, for instance, if I take AB is 2 dB, so that's my ratio. AD is 2 or divided by dB. This ratio on this side, it is going to be equals to AE divided by EC. So AE divided by EC. So this is what the theorem tells us. So because AD here corresponds with AE on this other side, and then DPE corresponds with EC. So therefore it says if you take the ratio of AD to DP, it's going to be equals to AE to EC. But this is only if the line is parallel. That's why the parallel line is very important. So that's what this theorem tells us. And then obviously we are saying that every time we're going to use a statement, we need to couple that with a reason. And the reason for this one, luckily enough, this theorem has got a name. So we are just going to say we are using the proportionality theorem. And then we say comma, then we say what allows us to use this theorem. So the only thing which allows us to use the theorem is the parallel line. So that's why we must quote which lines are parallel. So DE is parallel to BC. So that is the proportionality theorem. So that is the statement. So this is the statement of the theorem that the two sides are divided proportionally. So the ratios or the proportions are the same. And then this is our reason. So every time we are using statement, we must couple it with a reason. Okay, so that is what the proportionality theorem tells us. Now then you ask, okay, is this the only proportion I can take? And then obviously the answer is no. I could have said, okay, right now I said AD over DP. I could have said AD, so let's take another one. What if I say AD over AB? So AD over AB. So I'm going to say also is equals to, now on this side, it's going to be equals to AE over AC. AE over AC. Same reason, proportionality theorem. It's just taking a different ratio. And then obviously, I could start with the longer side. Okay, let me take another color. So I could say, what if I say AB over DP? AB over DP is equals to, then to correspond to AC over AC. AC over AC. So these are the different ratios that I can take. So there are 3 of them. In total, I can say there are 6, but the other ones really is just a matter of inverting. So you say DP over AD, EC over AE. So they're just very much the same thing. So these are the 3 ratios I can take. So which means whenever I'm encountering this theorem, I can just choose which side I'm going to take. And obviously, sometimes it's going to depend on the information you have. Whether if I'm looking for AD, then I say AD over DP. But I can only say AD over DP if I know DP when I'm looking for AD. Okay. So that's what the proportionality tells us basically. Okay. So which means you need to look for which lines are parallel that are allowing you to use the theorem so that you can write them next to the reason. And then you take your ratios. So that is what the proportionality theorem says. Let's look at an example. It's always nice to do an example to make sense of these things. Okay. So in the diagram below, we've got triangle ABC with DF and E on AB, BC, and AC, okay, respectively, so that FDEC is a parallelogram. So remember to read this information every time you're doing your practice questions or exams. So you've got a parallelogram here. You keep that in mind. That's okay, I've got a parallelogram. In case we have to use those properties of parallelograms. We are told that AD is 10. So I'm going to put in my diagram. AE is 9. BF, there is BF, it is 12. FC is 8. So this is all given information. It's always nice if you put them in a diagram. Okay. Now the first question is asking us to find BD. So there is BD. There is BD. Now, I need to take a ratio with BD. Now, there are a lot of parallel lines here, but let's look at BD. If I say BD over DA, because you see that these lines are parallel, that is DF and AC. So if I say BD over DA, then on this side, it's going to be equals to BF over FC. That is my statement. And then I write the reason. I'm using the proportionality theorem. And remember, you need to say which lines are parallel that are allowing you to use this theorem. So it has to be, this is DF and AC. So I write DF is parallel to AC. Now let's see now. BD, that's what I'm looking for. DA is 10. BF is 12. FC is 8. Now you see now the only unknown here is BD. So I'm going to take the 10 and cross multiply there. So BD, then I'm going to have 12 times 10 divided by 8. That is 120 divided by 8, which is 15. So it means BD is equals to 15. Okay, 15 units. In this case, they didn't give us units. So therefore, it means BD, we can just say BD is equals to 15 units. So I'm going to come to BD now, and I put 15. Once you've found something, it's always best to put that in your diagram so that you don't end up with a diagram which looks very raw or it's like it's missing a lot of information. So it's important to put it in your diagram. Okay, let's look at the next one, CE. Now the next question is asking us to find CE. Okay, there is CE. So again, I need to create a ratio with CE. Now, if I say CE over AE, that will be equals to BD over DA. Now I'm using these lines because these lines are also parallel. These lines are also parallel. So I say CE over EA CE over EA, we said it's equals to BD over DA. And then again, we need to provide a reason for our statement. We are using the proportionality theorem. And which lines are we using? We're using DE is parallel to AC. Okay, so CE is what we are looking for. EA, we said is 9, that is 9, is equals to BD, which we found as 15, over DA, which is given as 10. Then again, I'm going to cross multiply there. CE is equals to 9 times 15 divided by 10. That's 135 over 10, which is going to be 13.5 units. So CE is equals to 13.5 units. Okay. So you see, every time my answer must come with this. That's my statement. There is my reason. And then the rest here is just algebra. That is my answer. Okay. But every first line should actually come with a reason. If it's directly from some theorem. Okay. Let's look at the next one. Example 2. Now, let's read the information that is given to us. So here they tell us that AD, okay, I'm going to write this as a fraction, over BD is equals to 2 over 3. What you need to remember about fractions is that this does not mean that AD is 2 and BD is 3. It just means that their ratio in simple form will be 2 over 3. So now it makes it difficult for us. We cannot come here to AD and put 2. So instead, what we do, we're going to introduce a variable here. It doesn't matter what variable is. Just make sure you don't use these vectors which are here. Let's say I use x. So I'm just going to say 2x and 3x, which means AD is 2x, DB is 3x. Okay, so the x's there are there to preserve the ratio. Okay, let's look at the next one. BC over EC. So BC over EC is equals to 7 over 3. Now I'm going to use a variable again, so I cannot use the same one, as to end up meaning that EC and BD are the same. So let's rather use Y. So BC is 7Y. So now BC is the whole of this side. That is 7Y. And then EC, there is EC. EC is what? It is 3Y. Okay, so we've actually captured all the information we have. Now, obviously, if EC is 3Y, it means that this BK here, BK is 4Y, because they should combine 3Y and 4Y should give us 7Y. Okay, so there's my diagram. Now I can focus on that. Now, what is the question asking us? Okay, they're looking for CP over PT. So whenever you're looking for something, let's go and check what that CP over PT looks like, and if it does relate to any theorem or whatever the case is. Now there is CP. Okay, before that, because this line is parallel to that, let me just put parallel signs here as well, because this is one line, so it's parallel to the whole line. So we are looking for CP divided by PT. I think if you look at that, you immediately see that CP over PT will be equals to CE over EK. Luckily enough, we know CE, it's 3Y. We do not know EK. So which means once we have EK, we are actually sorted here. So which means our goal now is to find EK. Now, obviously, we are not going to use the same triangle to find EK, because in this triangle, we do not know CP and PT. Hence, we are looking for EK. So let's go to another triangle where they are parallel lines. And the triangle I see here is this one, ABE. Now, if you look at this triangle, let's see if we can find EK. So we can create a ratio here because these lines are parallel. So we can say EK over the whole BE. Because now you see, I do not know BK. I can't say EK over BK because I also don't know BK. So it's best to say EK over BK. Let me put that down. EK over KB. So on this side, it's going to be equals to what? AD over AB. And then, like I said, you need to put your reason. So we are using the proportionality theorem. Now we are using DK and AE. Those are the parallel lines. DK is parallel to AE. Right. So now let's see what we have. Okay, EK, we do not know EK. KB, wait, did I say KB? EK, EP, that was EP, not KB. Remember, we said we are using the whole line. We said EK over EP is equals to AD over AB. So that's EP. So EP, we said is equals to, that's the whole of EP. So that is 4Y. And then AD is 2X over AB, the whole of AB now. The whole of AB, there is AB, which means it's 2 plus 3 there. So we've got 5X. Okay, and there we can cross multiply there. So EK will be equals to, so okay, this is 2 over 5, the x's will cancel. So we've got 2 over 5 multiplied by 4y. Then this is 8y over 5, which means we have found EK. We have found EK. Now remember EK, there we were looking for EK. That's the only thing we needed to be able to answer the question. So there we were looking for EK. Now let's go back to CP. So we said CP over PT. Now we are answering the question now. CP over PT is equals to, and then it says it's going to be CE over EK over EK, and then again, this is our proportionality theorem. Now, which lines are we using here? We're using this line. That's PE and DK. PE is parallel to DK. Okay, so which means what is CE? Remember, CE was 3y there. We said it's 3y divided by EK. We found EK to be 8 over 5y. So the y's will cancel. So you've got 3 divided by 8 over 5, which will give us 15 over 8, because it's 3 times 5, which is 8. Which means CP over PD is equals to 15 over 8. So that's what the question was asking of us. Okay. Right. Let's try another one. Now, if you look at this diagram, got AC parallel to XZ and PD parallel to DZ. We are asked to prove that BC over YZ is equals to DA over DX. Now we have to prove something, so you have to go and check, have a look at one of them. So let's say, for instance, I look at BC over YZ. Okay, there is BC, there is YZ. That does not look anyhow related to proportionality theorem. Let's look at DA over DX. There is DA, there is DX. Now that looks like proportionality theorem. So let's try and see what we can get from there. So what if I say DA over DX? Now that will be equals to what? That will be equals to DB, because there is DB, over dy. Okay, so let's write that down. dA over dx is equals to dB over dy. I'm using my proportionality theorem here. And I'm using these lines here. So I'm using AB is parallel to XY. Okay, so that's my statement. Now, remember, I want to find a way to link dA and dx with this BC and YZ. So now I'm at dB over dy. dB over dy. Now let's look at this triangle DYZ, this one. If you look there, you'll see there are parallel lines, these ones. Now, if I say here, dB over dy, I think we can agree that on this side, it's going to be equals to PZ over YZ, if I'm using these parallel lines. Okay, let's put that down. dB over dy will be equals to PZ over this one, which is YZ. Again, here I'm using proportionality theorem, but I'm using these lines now. BP and DZ. So BP is parallel to DZ. Okay. Now, if I look at what I've done now, say dA over dx is dB over dy, and then dB over dy is equal to PZ over YZ, which means now dA over dx is equals to that. Let's see how does that help us. So now I can link these two. So I can say dA over dx is now equals to PZ over YZ. Now, if I look at what I have to prove, okay, I've got dA over dx, I've got YZ. But here I've got BC, but here I've got PZ. So let me look at BC and PZ and see how they are linked. There is BC, there is PZ. Now, how are these two linked? Well, if you look at this shape here, that is a parallelogram. If you look at that shape here, this is a parallelogram. Because this side is parallel to that, this one is parallel to that, which means now you know that opposite sides of a parallelogram are equal. So let's put that down. BC is equals to PZ because these are opposite sides of a parallelogram. Then we are done. So which means I can replace PZ with BC. So I've got dA over dx. Instead of PZ, I'll put BC over YZ. So there, I've shown what they're asking of us. So dA over dx is equals to BC over YZ. So what is key here is always check what you have to prove, and then you go to the diagram and see how does it relate to maybe proportionality theorem if you see that you've got these triangles. Okay. Now, then there are these ratios, these ratios of areas of triangles that we come across. So I just want to discuss, discuss them generally, and then maybe look at an example. So what we have to look for every time we're dealing with these ratio of areas, where you have to find the ratio of, say, area ABC over area ACD, whatever the case is. The first thing we have to look for is, do those triangles have equal heights? Now, how do you see if triangles have equal heights? Well, one, what you have to do, look at those two triangles. I'm going to draw an example here. Look at those two triangles. Okay, let's say this is ABCD. Let's say, for instance, I'm looking at area of triangle ABD here, divided by area of triangle BCD. Now, how do I know if they've got the same height? Well, if you look at ABD here and BCD, one thing you have to look for, do they have a side which they share? Not the whole side, but where we can say they are lying on that line. Is there a line where their sides lie, where both their sides are lying on that line? Is there such a line such that both of them have got either the whole line is their side or part of the line is their side? So for instance, the line here is AC, and then this triangle has got AB on this line, and then this one has got BC on this line. Okay, that's the first thing. And if there is such a line, focus on that line, and then you check that from that line, the other point of those triangles, is it common? So this is the common vertex. If that is the case, then we can think of those triangles as having bases on that line. So their bases are here, and then that is their highest point. So those triangles will definitely have equal heights. So what we are going to do then, you just call their heights H. It doesn't matter what you call it, so I'm just going to call it H. Because definitely we are sure that those triangles have got what? Equal heights. So that's how you know if triangles have got equal heights. So how does that help you? Well, you don't have to know the height if you're looking for the ratio of areas. You can just use your area of a triangle, which is half base times height. So for instance, for triangle ABD, the base will be AB, and then the height will be H. Then for triangle BCD, the base will be BC, and then the height will be H. And then you see the heights will cancel each other as well as the halves. So you end up with AB over BC, which means the ratio can then be determined if we know this side, if we know AB and BC. So the important thing from what I'm saying here is, how do we actually recognize, or how do you see if they've got equal heights? You check if they've got a sides where a line where their sides are lying on that line, and then from that line, do they have a common vertex? If that's the case, then you conclude that they've got the same heights. Then you rest assured that you can then use half base times height, obviously using that side as basis. Which means here we could do the same thing if we are looking, say, for instance, area of triangle ABD. So still this small triangle here, and we are dividing, say, by the area of the whole triangle now, ACD. Because both ABD and ACD, they are lying on this line and their highest point is there, which means they've got the same height again. So I'll say half the base of ABD is AB, and then I'll say times height. For the bigger one, the base will be AC, and then multiplied by height. As you can see, this will cancel, so the answer will be AB over AC. So this is how you actually check. So you look, every time you have to determine these ratios, check your triangles if they've got equal heights. And another thing to remember now, if two triangles, if the triangles we are looking at, they are between parallel lines, if the triangles are between parallel lines, then they have equal heights. Because even here, it's just a matter of saying, okay, if this, I've got a line there that is parallel to that one. So because these triangles are both perfectly fitting in those parallel lines, you can again just say, okay, they've got equal heights. They've got equal heights. Okay. So that's the first thing you look for. Do the triangles have got equal heights? Let's say they don't have equal heights. What can you check for? Well, you can check if those triangles have got common angles or if they've got equal angles. So I'm just going to make an example here. Let's say I've got a triangle like that. Let's say I've got A, B, C, D, E. And then we are looking, say, for the area of triangle ACD divided by the area of triangle ABE. So you go and look at those. Obviously, if you look at ABE and ACD, there is no way they don't have equal heights. Because if you look at this side, the highest point of this one is E, the highest point of that one is D. So they don't have equal heights. So that's why we also need to know what else can we do? You check if they've got a common angle. For instance, ACD is the bigger triangle and then AEB is this one. And obviously the common angle here is A. Now, if they've got a common angle, then you can use your area rule. Remember, the area rule says the area of triangle is half multiplied by two sides, and then multiplied by the sine of the inclusive angle, which means you're going to say half for ACD, the bigger one. It's going to be half AC multiplied by AD, and then you say sine of A all over. For AEB, it's going to be half AB times by AE, then times by the sine of the angle. So we don't even need to know the angle because it's going to cancel, the halves are going to cancel. So just like with the heights, if there's a common angle or if they've got equal angles, you can use those angles without knowing them, because in any case, if you use the area rule, there's going to be that cancellation which is going to happen there. Okay, so those are some of the things you can look for. Let's look at an example very briefly. Right, so in this case, what do we have? Right, we are told that R is a point on AB, S and P are points on AC such that RS is parallel to BP. Okay, I'm going to put parallel there because this line and that line is basically one line. This one is one line. They say P is the midpoint of AC. So P, remember now, which means AP, you can write this down so that you don't forget. AP must be equals to or is equals to PC. What do they tell us? They say AR over AB, we've spoken about this. AR over AB is equals to 3 over 5. I said just introduce a variable there. So AR, that is 3x. Now AB, we are told that AB, the whole of AB is 5x, which means we can just say this is 2x. So that if you add those two, they give you 5x. That is all we are given here. Now, the first question is asking us to find AS. So you're going to get the diagram, AS over SC. AS over SC. Doesn't look like directly from proportionality theorem, but let's see what we can do. Okay, what do you know about AS? Well, in this triangle here, we can agree that AS over SP is equals to AR over BR. So let's write that down. AS over SP is equals to AR over RB. We are using proportionality theorem. Then we are using this RS and BP. So what do we have here? So we've got AS over SP. Now remember that's AR over RB. AR is 3x, RB is 2x. So which means we've got 3x over 2x. It's going to be 3 over 2. So which means then let's go to our diagram. We do the same thing we're doing here, but now we're going to use different variables. So AS is 3, so I'm going to say 3y. SP is 2, so I'll say 2y. So now I know AS and I know SP, which means I know AP. But now remember that we noted here, because you see now we have AS, so we've got this part. We just need SC now. There is SC. In SC, we just need PC. But we know that PC is equals to AP. This was given to us. which means it's going to be 5y. So we can just put 5y there. This was given. There's nothing much there. We were told that P is the midpoint. So do you see now that we can therefore say it means that AS over SC, when AS is 3y, SC will be 2y plus 5y, which will be 7y, which means it's going to be 3 over 7. So there is AS over SC. Right. And then they say RT over TC. RT over TC. Now, RT over TC. Now, this looks like it's directly proportionality theorem if you look at this. So we can say RT over TC will be equals to what here? SP over PC. So RT over TC, SP over PC. Do not forget to put your reason. We are using TP and RS. Okay, let's see now. RT over, what is SP again? SP is 2y. What is PC? It's 5y. So it's going to be 2 over 5. So RT over TC is 2 over 5. So I'm going to put 2 here. Okay, let me just say Z over 5. Z. You see, I make sure that I do not use the same variable. Okay. Now the last question, that was my focus on this one, but I had to pass through the other ones. We are looking for the area of triangle ARS divided by the area of triangle ABC. Remember now we said we need to check, do they have a common height or do they have a common angle? So where is ARS? ARS. So ARS is this one. This is the smaller triangle there. And then ABC is the bigger one. Definitely, this cancels the possibility of common height. They cannot have the same height here. The other one is very big. It's very long. The other one is rather short, if you look at that. So they can't have the same height. So, but what do they have? They have a common angle there, which is angle A, right? So which means for ARS, we can use the area rule. It's going to be AR, AS, sine A. AR, so it's going to be half AR times AS multiplied by sine A. Like we said, you don't need to know the value of the angle. For the bigger one, ABC, it's going to be AB, AC, sine A. So half AB, AC, sine A. Now sine A and sine A will cancel. Half and half will cancel. So you end up with AR over AB, AS over AC there. So let's see, what do we know? AR, we know AR is 3x, AB is 5x. So this is 3x, 5x. What about AS and AC? AS, there is 3y. AS is 3y. AC will be 5 plus 2 plus 3, which is 10y. So if we have 3y, 10y. Okay, x and x will cancel, y and y will cancel. So 3 times 3, that is 9. 5 times 10, that is 50. So the ratio of these areas is 9 over 50. So that's basically how we deal with those areas, okay? And then I want to have a look at the similarity theorem now. What does the similarity theorem tell us? Okay. So we say polygons now. If two polygons or two shapes are similar, there are two requirements. I'm going to run through this one. The first thing that must happen is that they are equiangular. So you look at any two shapes, it doesn't have to be triangles. They are equiangular, which basically means that they have angles. In both of them, there are angles that are equal to each other. And then the second one is that the sides are in proportion. So these are the two requirements. The two shapes must have equal angles, and then at the same time, they must have sides that are in the same proportion. Now, we already know what a proportion is. It means if you take one side and divide by the other, you should get the same answers. But this is where we're focusing on. For us, for triangles, only one of these conditions need to be checked, which means these conditions imply each other. This is what we focus on. There are two requirements, but for us, we are saying we don't need both of them. If one is true, the other one is automatically true, which means you can just say, if they are equiangular, if triangles are equiangular, we don't have to check the second requirement. We can just jump straight and say they are similar. We can use the second requirement. Likewise, we are saying that if the sides are in proportion, then we can just jump straight and say they are similar. We don't have to check the second one, but we can use it, okay? So this is the beauty of this theorem. So for triangles, we just need them to be equiangular. So this is what the theorem says. The corresponding sides of two equiangular triangles are in the same proportion, and therefore the triangles are similar. That's what I was saying, that let's say here, let's say A and D are equal for the sake of simplifying this. So you see, if you look at these two triangles, they are equiangular. So because they are equiangular, the theorem tells us that once you can show that they are equiangular, so you just need to show that they are equiangular. If you have shown that, then this theorem says you do not have to check whether their sides are in proportion. It tells that the sides are in proportion. You don't have to check that. You can just straight away conclude that the triangles are similar, but you can use the fact that the sides are in the same proportion. Okay. And then so now, so which means how do we then prove? That's what I was saying. How do you prove they are similar? Well, you just find two angles that are equal, because obviously the third ones would be equal. So you look at your triangles, find two angles that are equal in both of them, and then you conclude that they are similar. I want us to look at an example before we run out of time. So here we are told that ST is a tangent. That is all we are told. Everything else is on the diagram. These lines are parallel, those two are parallel. What are they saying here? Let's say we must prove that STW. Now STW, that is STW. Prove that this triangle is similar to SRT. So I'm going to draw it using another color. SRT is the bigger one. Remember what we said, you just need to, if the information is about angles, find two angles that are equal. The third one is obvious. It's always very nice when there is a common angle because it makes your life easier. Okay, now here, SRT and then SWT. I think we can all agree that angle S is in both of, if you blue triangle and the red one. So I'm going to say, okay, my first set of angles, angle S is equals to angle S because it is a common angle. That is my first set. Two, I need to find another one. Now in the blue triangle, you see there I've got T2. And remember, this is a tangent. So tangent chord. I'm going to use the tan chord theorem because this chord subtends angle R. So which means angle T2 is equals to angle R. I'm using the tan chord theorem. I love it when you've got a common angle because it means you just need to find one other angle. And then the third one you just state. So we've talked about S, we've talked about T2. The remaining one is this one, which is SWT. So you just state that one, SWT. And then in the orange triangle, the remaining one is, okay, we've spoken about S, we've spoken about R. So the remaining one is this T here, STR. So this one you just state, there is no reason, but your reason is just going to say third angle. So the third angle or the third set of angles or pair will have to be equal. They have no choice. Then you can say, therefore, because now you've shown that they've got equal angles, which means they are equiangular, then you just say, therefore, STW is similar to triangle SRT. The reason we say they are similar is because they are equiangular. So angle, angle, angle. Because remember, the theorem says, if you can show they are equiangular, then you are done. You just say they are similar. You don't have to check the sides, but you can use the sides. So what does the theorem say? The sides are in proportion. Okay. Now look at what they've done here. They say hence, meaning using what we've done above, right? ST squared in terms of the sides of these triangles. Now you see, because we have shown that these two are similar by showing they are equiangular, then we can use their sides. The theorem says this, the corresponding sides are in proportion, which means if you look at ST here, I like to do that. If you look at ST here, it corresponds with SR on the other one. So then I'm going to take a proportion. ST over SR is equals to. Now, because what I'm required to write here has got two STs, they said ST squared. I need to find another ST, or there's an ST on this side. So now I'm going to say SW divided by ST. I need to make sure I'm starting with the same, because I started on this side. Even on this ratio, I need to start on that side. So that's why I'm saying SW over ST. So I'm taking a ratio. Why am I taking that ratio? Well, because I know that the sides are in proportion, since I've shown that the triangles are similar. So I'm going to cross multiply here. ST times ST, that's ST squared. SR times SW, that's SR multiplied by SW. That's why they said I must write. They said I must write ST squared in terms of the sides of this triangle, which is SR is a side, SW is a side. Okay, thirdly, they say hence again, so meaning we're still on what we've done above. Hence, calculate WR. What have they given us? They've given us ST and SW. Now I'm going to take what I have above here. So there is ST, ST squared. So ST is 6, so I'm going to say S6 squared. Okay, SW is 4, so I don't know SR. SW is 4. So this is 36 is equals to, this is 4 SR divided by 4. It means that SR will be equals to 9. So this information I have here allowed me to find SR, but they are asking for WR. So let me go back to my diagram. So we are saying SR is 9. What else were we told? We were told that SW is 4. So do you see that? SR is, the whole of SR is 9, but SW is 4, which means WR has to be 5. WR will be 9 minus 4, which is 5. All these are centimeters. WR is 5. Okay. Now this state with reasons one pair of similar triangles from the diagram. One thing I want to mention that you must never forget here, which I think I skipped a bit, is that I said here proportionality theorem implication of similar triangles. What I want you to always remember here is that if you look at a triangle and you are thinking proportionality, so let's say A, B, C, D, E, every time you've got that kind of proportionality vibes thing going on there. Every time when this happens, you've got two triangles here, this small one here and the bigger one. Those two triangles, A, B, C, will always be similar. Please don't forget that. You don't even have to prove that unless you are required to prove it. But A, B, C will always be similar to ADP. You can go and check that. You'll see that their angles are, they've got a common angle here. And then this one will obviously be equals to that. They are corresponding, and that is equals to that. So this small triangle is always going to be similar to the bigger one. So you see here, they say, state with reasons one other pair of triangles that are similar. So now I'm looking at this here. I see proportionality. If you look here, I've got proportionality going on there. So I can say RVP, triangle RVP is similar to triangle RWT. This is one pair. Obviously, I could look at the other proportionality. If I look here, SRT, you see here, I've got proportionality going on. So I could say SQW is similar to STR. Okay, so any of those, I'll just say, they said only one pair, but I decided to write two of them. Okay, I think I can still use 5 minutes and then close. Okay. Now, so remember, I said there are two requirements for similarity, but you only have one for triangles. For any other shapes, there are two, but for triangles, you just need one. It's either you prove they are equiangular and then you can use the sides like we've just done now. The other one is the converse, which says you can prove the sides, then you use the angles. So it says if the sides are in proportion, so if the sides are in proportion, then the triangles will be equiangular. So therefore we are similar. So which means the theorem tells us that if you can show that the sides are in proportion, so let's say AB and DE correspond. So AB over DE, if you can prove that AB over DE is equals to AC over DF, which is also equals to BC over EF. If you can prove this, then we can immediately say that triangle ABC is similar to triangle DEF because the sides are in proportion. So we don't have to check, the angles anymore. What we have to do, we can use them. Just like when we had angles, we did not have to check the sides, but we could use the sides. Okay, we'll do an example of this one because I know it's most of the time it's very much ignored, but it's very important. So which means what we have to do in this case, you just have to prove that, like I was saying, the sides are in proportion. So these ratios are the same, even if these are numbers. So if it's 1/2, 1/2, 1/2, then you can say those two triangles are similar. Let's look at an example here. They told us PT is 6, TV is 4, VX is 4 units, XW is 7, WP is 5, TW is 2. And then they say we must prove that triangle PTW, we must prove that it is similar to PXV. You see, they did not say PVX, they said PXV. So that gives you a clue in terms of which side you must look for. So now let's look at our sides here, 23.1. So if I look at PT, let me check PX. PT is 6. So PT over PX. And then PX is 5 plus 7, which is 12. So I get 1/2. Let me try another side. Let's say TW and XV. TW is 2. XV is 4. And this also gives me 1/2. Let me check the other side. PW and PV, not present value. PW and PV. PW is 5. PV is 6 plus 4, which is 10. So you see that if I'm taking these corresponding sides, I'm getting the same answer. And the theorem says if the sides are in proportion, then the triangles are similar. So we can conclude, therefore, that triangle PTW is similar to triangle PXV because now the sides are in proportion. Now here we have used the sides to prove proportionality. Then, remember we said now we don't have to prove the angles, we can just use them. What that means is that because PT corresponded with what? With PX. So it means that T1 will be equals to X. Because now PT, look at X, look at T1. T1 is between PT and TW. And then X is between PX and XV. PT corresponded with PX, TW corresponded with XV, which means T1 is equals to X. Likewise, W2 will be equals to V. And the reason is because W2 is between PW and WT. And then PW corresponded with PV. Then TW corresponded with XV. So which means V is between those and then W2 is between those. Okay, I think in the interest of time, I'm going to have to close there. This question you can try, but you see it says prove that PL is a tangent to the circle passing through PWT. Let me just do that one. PWT, so you always draw that circle. It doesn't have to be a perfect circle. They say prove that PL is a tangent to this circle. Now, if I look at this, I can smell Tanko theorem. Because now if this line is a tangent, it means P2, I need to prove that P2 is equals to T1. Then this line will be a tangent. But how do I prove that? Well, what do I know about P2? Look at P2. P2 is alternating with X. So I'm going to write P2 is alternating with X. So these are alternate angles. Vx is parallel to PL. But what do I know? I know that X is equals to T1. So X is equals to T1. I already said that because of the similar triangles. So because PTW is similar to PXV. You see that now we are done. We have shown that, therefore, P2 is equals to T1. Now, if P2 is equals to T1, it means that PL is a tangent. We are using the Tan-Cot theorem in reverse. So it's the converse of the Tan-Cot theorem. Okay, so that is how you do that. I think in the interest of time, I'm going to stop there. There are some questions I've put for you there, some practice questions there. You can look at those, they will be very helpful. They've got answers there, okay? They've got answers at the back. So you can have a look at them. Okay, I think this is where I'm going to end. Say, are you there?
Yes, sir.
Yes, yes. Oh, Dr. Hansraj, are you back, sir?
Yeah, I'm back.
Yeah.
Okay, man. Thanks for a wonderful lesson. And in the interest of time, I don't think we're going to have, time for questions. So
Yeah.
we're just going to move straight to, we're just going to wait a bit and then move straight to the science show. But thanks, man. Please send me the slides as well as the one you were using
on
Monday.
Yeah, no, yeah. I'm going to send both of them. Yeah, I'll email both of them. Thank you, sir. Thank you very much.
All right, thanks, Vezi. Sharing.
Okay, so we are back. Hello. So we are back from a short break, which I hope you enjoyed. And now we are going to start our magic show. And I was just talking to the audience here, and we talked about experiments. And we thought about different experiences that we have with experiments. Some experiments, you've seen them many times, and maybe then they are boring, okay? And then there are experiments which really can surprise you because you see something new. If you see something new, you can learn it. You can learn something, okay? And this is fun. So I want to show you some experiments, and then I would like you to position them in a coordinate frame. If you look at the board here, can you see this? There is an axis which has on top fun, okay, and here boring. Okay, I hope one can read it. And on the x-axis, I put on this side easy, and here difficult. Okay. I hope it is visible. Let me just check in the, this seems to be a little bit difficult. I asked my assistant, Mrs. For each experiment where we are. Of course, we want to be in the corner of fun and easy, but sometimes things go wrong and we become we get a difficult experiment, and certain experiments have to be difficult by nature. Imagine, for example, the detection of gravitational waves. Okay? Gravitational waves occur if big, massive objects collide. Okay, something like neutron stars or even black holes can collide, and then there is a ripple in space-time, in space, and it propagates, and it's a wave which kind of oscillates and makes distances smaller transversely to the propagation direction, and this can be measured. But it's on a very, very, very tiny scale, and it took people very long, maybe since 1916. It was now the measurements were the detection was confirmed in 2015. So that's nearly 100 years. All right, and that's an experiment that's very difficult, but it's also very much fun. So it would be very much up here, but also very much on this corner, right? Why is it so much fun? Because we learn so much about the world around us. Okay, so I want to start with a very simple experiment, which works like this. Maybe you want to open the door. And you help them. They don't. So. I want to let this cylinder roll. And what would you expect what the cylinder does if I let it loose now? What is the expectation? What do you think? In which direction will it go? Down the slope. Huh? That's what we think. It goes up. So how did that work? Is there a magnet in front? Let's see. So we try to find out why this is like this. No, that's just a cable. Nothing exciting. Okay, so why did this thing go up? Maybe we find it out if we look inside the cylinder. You know, because the cylinder is somehow a little bit prepared. I want to show it to the audience. Do you see something in there? There is a weight. We plugged a weight inside. Okay, so in the case that the weight is kind of heavier, so exerts a higher force than the gravitation of the whole cylinder leads it down, which depends on the incline of the plane. It rolls in the opposite direction. Okay, so this is what happens if I take it this way. And you see that it starts rolling this direction. Okay, so this is an experiment, and we can now put it on the scale. Do you think this was fun or boring? Fun? How much should I put it up now? Low. Okay. Here? In the middle between fun and boring? Is fun. Yeah, okay, yeah. So 1/3 fun. Yes. And how difficult and how easy? Easy, easy, easy. Yeah. Is that fine? Okay, so I just I call it rolling cylinder. A cylinder rolling up. Okay, so that's our first experiment. Now the next experiment that I want to do is the following. I have here a tube, and in this tube there is a marble, right? And you can see that the marble is rolling around. I incline it a little bit, and then there is a kind of plastic, a piece of plastic, polystyrene, which is very light. And now, what do you think if I turn this on its head? Which of the two particles will hit the bottom first? I mean, if this becomes the bottom, so I will rotate this thing. The marble, huh? Who is for the marble? Who thinks it's the polystyrene? No. Okay, we'll try. No, it's clearly the marble. So this is not very fun, very much fun, but we can make it more fun if we start to pump the air out of here. Okay, and while we do this, I will actually show you another experiment, or let's see how much is it already kind of difficult to show to pump. So while my assistant, Mrs. Permel, is pumping the air out of this thing, yeah, is it okay? Yeah, I think it's okay. So now we try it again. So what we have done is we used the syringe to pump the air out of the tube. Okay, and now I will do the same thing. I will rotate it such that this becomes the bottom. And what do you think will the marble hit the thing first? Do you think that will happen? Do you think that the polystyrene hits first? Do you think that both hit at the same time? Who thinks that? Okay, the audience thinks, sorry. Okay, so at least I think there is a majority thinking that that they both hit the floor at the same time. So I turn it around and the marble came first. So we have to maybe this time it was the same. No, not really. So we have to evacuate it a little bit more, and later we will look at this again. So let me come to another experiment, which is using the following. So we have here a ball. Okay, this is a ball, small ball. Okay, and here I have a hair dryer or air blower, more precisely, and I want to balance the ball on the airflow. Okay, this is not very nice. So you can see that I can balance, right? So just to explain this, what we see is that the ball is dancing on the air, and we can understand it because gravity is pulling it down, and the air is pushing it down, right? But now I will actually slightly turn it to this side until they are in this position. And then you will still see that it hangs in the air, okay? And then the question is, of course, what keeps it in the air? Okay. We need the highest. So you see it starts rotating. Interesting is it doesn't fly away. It's one good thing, you know. If the air is flowing fast enough, I can really make it so that it is standing horizontally, that the air flows horizontally while gravity is vertically. All right. So I don't control it. Okay, could you see this in the audience? So the air is really balanced. And the question is, you know, at this time gravity is still pulling, but what is keeping it up? Any ideas? Is this working? Do we have to, do we have some paper sheets? Any ideas?
The ball was spinning.
Ball was spinning, yeah. Do we know any effect that if a ball is spinning, it does something special? Think of soccer. You know, if you are shooting a corner, what happens? There are people that can make the ball curve. You know? It's called the Magnus effect. You know? So it has something to do with the air streams along the ball and so forth. But here's a simpler explanation. If I blow between these two, these are two sheets of paper, and I just blow between them, okay? And you look what happens. Sorry. They stick together. Okay, they don't blow away like one would think. They clamp together. And our chemist colleagues know this very well. This is the Bernoulli effect. This is if there is a fast airflow in a direction, then there is always a pressure that is perpendicular to the airflow. Okay, as we can see here. And this is what keeps the ball in the air. So there is, in the beginning, there is airflow on both sides, but then gravity pulls the thing down until there is no more airflow here, you know, and there's a lot of airflow here. And then there is a pressure, there is a force component that pulls it up. It's the same thing that makes planes fly. Okay, so we learned something, hopefully, and I want to know was this fun or boring? Fun? More fun than the rolling up cylinder? More fun, you learned more. Okay, I go here, or the difficult part? Much more difficult, yeah, I would also say, but also not really difficult. Well, I mean, you can do it at home. Okay, I put it here, right? So this is the dancing ball. Okay, so now I have to look already on the watch, because I noticed that that I have still 10 minutes. That's wonderful, because I have so many things I want to show you. And the next thing is maybe something that is also very curious, because we talked about airflow. Okay, and here is a normal. It's a normal mask made out of rubber, right? Rubber material, and I want you to just pull this thing up. Maybe I compare it to you. No. Here as well. So we are going to just put this on the table. Ask the gentleman in front of us to lift it up on the handle. Okay, he can't, right? So you can try as well. So somehow we cannot lift this up, although if I take it at the edge. So there is no glue here. This is just air pressure. The pressure of the air molecules, you know, the air molecules fly around, they hammer against everything that they find. Okay, so they hammer from this side, but not from the other. That's why they hammer the thing against the floor. Okay, so we have here a case of air pressure, and it's just a simple mass. And what I can do, I can put it on the ceiling, right? And then I can make a small plastic, how do you say, tape around it, so that the edges don't fall off, you know, and no air comes underneath. And then I can hang this. And not only me, you know, if this is like 30 centimeters times 30 centimeters, it will be able to hold 900 kilograms. That's a lot, you know. So this is the one thing with air pressure. Okay? Let's go to the board again. What do you think? Is this fun or not so much? Is more fun than the dancing ball? I don't think so. Is it more fun than rolling up? Yes. So in the middle, right? And how difficult? Yeah, I also think so. Easier than the rolling up. Okay. Can I say something? I think it's more difficult. No, it's less difficult than the rolling up, because the rolling up, you can get it wrong and then it rolls fast down. So I say, is that okay? Okay, super. So this is the what was that? The rubber mass, the air pressure, the pressure mass. Pressure. Okay, if you can't write pressure mass. I write this good. Okay, super. So this is this, and now we come to the next experiment, which is which is a totally different thing. How much time do I still have? 7 minutes. Perfect. That's exactly what I need. So if you take a magnet, okay, so this is like a magnet, right? And you can see actually, okay, maybe we have to check this a little. Okay, so this is how would you describe this? What is inside here?
So iron fillings, something like that. Yeah, fine.
Iron fibers. Iron filings. So this is a liquid with iron filings inside. And if I push this magnet inside here, then one can very nicely see, if one holds it against the light, one sees the orientation of these filings with a center here at the south pole of the magnet and another center at the north of the magnet. And I just try to check whether you can see it in the camera. Maybe you can see it. Do you see the aligning? So it goes around like this from north pole to south pole and back. So this is the aligning, and it is a kind of an interesting thing because you know, it is exerting a force at a distance. You know? So this is the magnet, and if I put here another magnet, you know, I can see how it is. I can feel how it is pulled. You know, and how does it act at the force at a distance? How is that possible? You know, that something can act at a distance so easily. You know, I mean, gravity also does it, but I just want to point that out. And now the thing is that there are some interesting experiments with these magnets, and one of them is the following. So I have here a magnet with a north and a south pole. Okay, I hope you can see this. Maybe put it a little bit more down. Yeah, so this is this, and then there are some plates. Okay, and these plates are not magnetic, so they are aluminum. You know, nothing. So now I can use these plates to let this swing through the magnetic field. Okay, and what do you think happens if I do this? Well, okay, this was not the right fit, sorry. So this is like a comb, okay, and I let it swing through this thing, and it swings. You know, that's what a pendulum usually does. It oscillates, right? So give me a little bit more. Yeah. So now I will take another plate, which is like a solid plate. So the thing before was a comb, okay. And if I do this now, then the outcome is radically different because it just stops. Right? And now there's a third plate, which is like the comb, but it has these closed edges here. So everything is like connected. And if I do this, then it also stops. It swings more than this plate, but less than this. Okay, so there's more friction in this game. And the reason for that is that if you swing through a magnetic field, if your metal and the charges in the metal experience a changing magnetic field, then there is an electric field produced, and that moves the charges around. In this case, they move in circles, so-called eddy currents. And here they can move in circles, while in this thing, they cannot really move in circles, at least not on big circles, okay? And that's why this thing doesn't experience this friction, because of course it's moving around takes energy, okay? So this moves freely, while this one cannot move freely, okay? So this is something where we can learn, even though that might not be immediate. And what we can learn from it is we can actually change the magnetic field in such a wire. Okay, so the wire also contains charges that can move, right? It doesn't need to be magnetic material or anything. Main point is that there are charges that can move. And now I'm going to put this magnet inside the coil here, which consists of loops of wire. And if I move them back and forth, then you see on my charge meter that somehow something is moving. And I put the 0 here in the middle. But if there was 0 current now, then if I move it in, there is a current in the one direction. And if I move it out, which is also a change of the magnetic field, then there's a current in the opposite direction. so by just doing this, I can produce an AC current. Okay, and this is a motor. I mean, this is a generator. So I can actually kind of use a combustion engine with a piston to produce electricity. And there is other ways where you have a magnet that rotates. It's easier than doing this motion. Rotates and produces electricity, and that's a turbine. So driven by a turbine, you can produce electricity. Okay, it looks like this. I don't want to, because I'm at the end of my show, I don't want to show you the thing, but here's a propeller, and here in the middle of it, there is a magnet, and then there are coils around it. Okay, and then by rotating this magnet through the coils, or in the kind of in the vicinity of the coils, I induce a current. Okay, this is called induction. And in fact, if you have a changing magnetic field, then you produce a changing electric field, which in turn produces again a changing magnetic field, and that produces a electric field, and so forth. And the whole thing is called electromagnetic wave. It propagates. It can propagate through space, even if there's no medium in space, no other medium, it's empty, no air, nothing. It propagates through space. And one of the big things of, one of the big triumphs of theoretical physics was that we found out that the speed with which electromagnetic waves propagate is exactly the speed of light. And that means actually light is an electromagnetic wave, or very probably so, right? And it could be explained as such. So we can model light as electromagnetic waves, and then optics is just a subset of electromagnetism. Okay, so this is a nice thing, and we know all kind of experiments that have to do with it. But I want to show you one, if I may. I don't know. I'm already 1 minute over it, but we had 5 minutes load shedding break. Do I have another 2 minutes? Question to the organizers?
Yes, definitely.
Thank you. So maybe if you put the camera a little bit back so that they can see me. So this is a laser, and it's a very high powered laser. Don't know how many watts it has. It says here wavelengths 250 nanometers, and watts at maximal output. I can't read it without my glasses, but it seems to be something like 5 watts. That's a lot. You know, the highest lasers have terawatts. That's 10 up to the 15. So one with 15 zeros watts, and you can shoot right through metal and all kind of things. And I want to use this laser to shoot something through something. Namely, I have here a system of air balloons. Okay. In fact, this is 2 air balloons. Okay, and the one is inside the other. You can see that the outer air balloon is transparent, while the inner air balloon is kind of, what is this color? Purple. Purple, thank you. And I want to play a trick on this. Namely, I want to kind of explode the inner balloon without changing the outer balloon, you know? So, and I try to do that with the laser, hoping that the light, because it's transparent, is not absorbed on the outer balloon and hits the inner balloon. The inner balloon will heat up and then hopefully explode, okay? But so I need someone assisting me with this, who should actually carry the glasses, because I don't want to, do you want to do it? Okay, it's Mrs. Palmer. Okay, so please put on your glass. I hope this is a little bit dangerous. No, it's not really dangerous. I hope at least. But first I have to. So people are moving away from my laser beam. You can see it there on the wall. It's blue. Okay, and I'm going to shoot now. Hopefully something happens. No. Oh, good, nothing happens. Go close up. Maybe I should wear glass. So yeah, it might not work now. Maybe I need a lens.
But what we can do is just then make a dark more.
This is a good idea. But then maybe the outer one.
Yeah.
Oh, the outer one will be it. Okay. Was that the blue?
So just a dark more.
Dark is okay. Dark means the light is absorbed. Okay. So let's see what happens now. Let's see whether I can shoot on this. Oh, I'm shaking a little bit too much.
Is that working?
Yeah. Okay, so this was it from the physics seminar room. Thank you very much for your attention. Bye bye. Would be nicer to explore the big one. Huh? Yes, back to the organizers.
Thanks, Professor. Cele, do we have
Yes, we have the next presenter, Ajay.
yeah,
I've already,
oh yeah, I think
yeah.
I see him now. Okay. Okay, cool.
Yeah, you.
I'm here. Good afternoon, everybody. Can you hear me loud and clear?
Loud and clear.
Okay. I'm not seeing myself, but it's fine.
It's fine.
I'm
We
going to
see
share.
you.
You can see me. Okay.
Yeah.
Right. Let me just stop this here. I just want to. Okay, so I'm not seeing myself, but I just want to introduce myself and say welcome to all of the participants, the grade 12 students. And it's interesting to look at all the different aspects of science. And you just saw Prof. Konrad show you all the different types of experiments that you engage with. And here at the university, when you finish school, you learn some of the basic fundamentals, and then basically after that, you come to university and we teach you a little bit of advanced stuff so that you could apply yourself, in the open world. I'm sure at schools, to all the matriculants, university is a little bit different. The way we do things, you see our labs are much more elaborate, etc. So I am Dr. Bissessur. I'm one of the lecturers in the School of Chemistry and Physics. I'm an analytical chemist by trade, and basically I analyze anything and everything. So I'll talk a little bit more about that in my presentation. Let me just share my screen and I'll take you through my presentation for today. Please feel free to stop me at any point if you don't understand anything. I will be more than happy to answer some of the questions. Right, so welcome to students of Be a Scientist for a Week 2023. You can see this is what, when we do presentations, we call it a busy slide, but I deliberately put all of these things around to show you all the different aspects of chemistry. So on the left-hand corner, I'm sure some of you can see the burettes, the pink burettes, the burettes with the Erlenmeyer flasks, and that basically is a titration. You can see a pipette, so you can see all the different apparatus. On the top screen, on the top above University of KwaZulu-Natal, you see all the different colors, and that's where we look at flame analysis. We do quite a lot of spectroscopic analysis in analytical chemistry. And there's a nice structure of sulfur, which we look at inorganic chemistry, all right? Then you can see a whole lot of nice different solutions here. We look at wet chemistry, we look at qualitative analysis. And then if I go to the left-hand side where it says oil composition, carbon, hydrogen, nitrogen, oxygen, and sulfur, that's also got to do with analytical chemistry. And then below here, you can see the students working in a lab. And you can see we have at UKZN, we have very, very, very modern laboratories. And I'm going to show you a little bit more. So welcome to students of Be a Scientist for a Week for 2023. And our motto or our theme for this year is Chemists Provide Solutions, because obviously we provide, this is not only solutions in the physical state, but we also provide solutions to all your questions that you have. And you can see the nice periodic table where we have an understanding of all the elements. So we know this guy, Nelson Mandela, and I took this from a slide for Heritage Day. And I like what this slide says, that we can change the world and make it a better place. And it is in your hands to make the difference. So when you come to university, that's what we're trying to do. We are trying to change the world to make it a better place. We are trying to get cleaner water. We are trying to basically generate electricity that's, you know, from much more better systems rather than, you know, what we are facing in the world. And our late ex-president Nelson Mandela, you know what a world icon he is. I wouldn't say he was, but he still is an icon. And so I would say that making a change to the world is what chemistry does. You know, we have chemical changes and we make different products from different starting materials. Okay, so let's take you to the next slide. This is a nice picture, and I'm just showing you, sharing something with you. We take students to the International Chemistry Olympiad, and this was a picture of the students that we took to the Chemistry Olympiad, and this was held in Prague, in the Czech Republic. So the International Chemistry, and these are grade 12 students, by the way. So they represented South Africa at the International Chemistry Olympiad. So here in the School of Chemistry, I'm the head mentor for the South African team that goes to an International Chemistry Olympiad. And you would have written, and how to get into this, you would have written our National Science Olympiad exams, and then we have a selection. So this is communicated via your school. Right, so this is who I am, a lecturer, and I'm just going to go through the next slide. Now, I just want to ask you this, you know, the students that are in grade 12. Now, when you think about a career in science, physics, maths, chemistry, research, projects, what comes to your mind? I mean, what do you want to be? And I'm sure all of you have been filling those dreaded applications to university. And then you're thinking, do I want to do physics? Do I want to do chemistry? Do I want to do engineering? If I want to do engineering, what do I want to become? A chemical engineer, a physical, electrical engineer, computer engineering? But you've got to find out, right? So let's say I want to do something really out of this world, you know, something that can get you a good job and a top salary and work in a top facility like NASA. You know, so obviously that's where you want to head through, isn't that so? Now, then you want to do a project and you come to university, and then you come to me and you say, Dr. Bissessur, I want to do a master's degree with you, or I want to do an honors project with you. And then I give you this topic here, and I'm going to read this topic number 1, and I say, yeah, Mr. X, you are going to basically do a project, the use of a polydentate ligand, ethylene diamine tetraacetic acid, for the removal of calcium in hard water using a Richrome black tea indicator. Oh my gosh, what the hell is this? Now you read that word, ethylene diamine tetraacetic acid. I think it's probably the longest word in the dictionary for a word that exists. And I'm sure many of you have never heard of this word. And then another student comes to me and I say, oh, I've got a nice project for you. Transesterification of fatty acids for production to high quality biodiesel by magnetic impulse, high frequency cavitation processing. My gosh, stop. This is too much. So you see, you're at a point now where things are just being thrown at you that you don't understand. And this is what I'm trying to tell you at this point, right? what you want to become, what you want to do, and I'm going to try and unpack it for you in the next few minutes. Right. So some pressurizing questions that can assist you in the direction of your field of study, especially now in chemistry, right? But when you want to study something, you first ask yourself your question, what do I want to study? What do I want to become? How much do I want to earn? That's obviously the first question you want to ask, isn't that so? Where do I want to work? What is my passion in life? Do you want to sit in an office or do you want to work in the lab? Do you like working with your hands? Not many of you do so, isn't that so? Do I like solving problems or do I like working with people? So I'd like you to put this down, and then that will help you to gauge where you want to go and how you want to basically, where do you want to get to in terms of your life. So now the requirement, so we have this program in BSc Chemistry and Applied Chemistry at UKZN. So I'm talking specifically about UKZN and Chemistry and Applied Chemistry. So what is the requirement? I would say a decent pass in matric with excellent marks in maths and physics. So let's just say you are basically over the line in maths and physics with an average of 65 or 70%. That is what I refer to as a decent pass, notwithstanding that you've got to pass your other modules as well. Okay, so I would suggest you go to the university website, www.ukzn.ac.za, and you access the first year students information for first year students, not for 2019. Sorry, this is just a typo error. It's 2023. Okay, and you will find that there are various programs which are 3-year degree programs. So in the School of Chemistry and Physics, and I've also included physics and some other courses, but you can see we have chemistry and applied chemistry. You can do chemistry and physics, chemistry and maths, chemistry and biochemistry, chemistry and microbiology, chemistry and physiology, chemistry and environmental science. This is becoming a popular one. So the top, and chemistry and geology. So the top, I would say the most popular ones are chemistry, applied chemistry, chemistry, microbiology, and chemistry and environmental sciences, given all the crises that we have at this current point in time. Okay. This is a very busy slide. Don't worry about this. But this is basically, if you could just, this basically tells you the different courses that you take in chemistry. And don't worry too much about this. But if you look at a chemistry major, right, you'll see in semester 1, we do chemistry 110. And in semester 2, we do chemistry 120. So if you come next year to UKZN and you want to do a chemistry major, you'll have to register for chemistry 110. That's what we call it's the module code, right? And chemistry 120 is a code for first year chemistry modules that you will do in the second semester. And you can see each one carries 16 credit points. So when you do a module, you are given credit points. Now, you would want to do maths, you want to do physics, and you do what we call an elective. So maybe biology. And that's basically the first year sort of BSc that many students take to go on to many other courses as far as BSc is concerned. But to do a major in chemistry, you notice in first year you did Chem 110 and Chem 120. Now look at second year, you do Chem 210, Chem 220, Chem 230, and other courses as well. So in other words, you are majoring in chemistry. And if you look at level 3, we have chemistry 330, chemistry 310, chemistry 340, and chemistry 320. But you've got to do other courses as well, right? So that is what is called a major in chemistry. And the same applies to the applied chemistry course. So I don't want to delve too much into that, but you can go through this and this will help you. It is available online, and we will make this available to you to have a look at. Right, so let me go on and let's talk about the field of chemistry. Now, you guys know that everything that you do from the time you get up in the morning, whatever you do is chemistry, right? You get up in the morning and you firstly want to go to the bathroom, you want to brush your teeth. You need polymer, you need a toothbrush. So your bristles is also a polymer. Then you need toothpaste, titanium oxide, and then you have a gel, which is So all of these things are chemistry, okay? So you yourself is basically chemistry. Yourself, you're made up of all different types of chemical components. And these are the different types of chemists that we find in the world, okay? And you can see a whole range of them, and they work in different places. So you can find a niche area. So you're not just a chemist, but you can be an analytical chemist like myself. I do analysis in the lab. I analyze water, I analyze plants, I analyze soil, I look at different types of solvent systems, etc. Then we have organic chemists. Organic chemists now basically look at all the different types of components you have in plants, and you want to basically get all different type of components. So you can fit into a different type of, and I highlighted one here called a computational chemist. That's a very, very interesting field. And one of my colleagues that's listening on this chat, her name is Dr. Tishana Singh. She's a computational chemist. And she predicts, for example, how chemical reactions will take place, the feasibility, the energies that are involved. And they model how different reactants come together to form things. And that's a very important part of chemistry. So you can bring in your computer knowledge, your IT knowledge, and you can basically put it together with your chemistry knowledge. So you see, chemistry is not restrictive. You can do it with, so you have, and there's some interesting ones here. A formulation chemist, you can formulate, these days you have detergents, you have cosmetics, the cosmetic field is big. Then you become an environmental chemist. In South Africa now, there's been a big hoo-ha about our water being contaminated. The environment is being contaminated. We need you guys. We need you guys to go and analyze things and look at the environment. You even have a detergent chemist, okay? A nanochemist, an electroanalytical chemist, a material chemist, and then we have an oil chemist, okay? So we have lots of different types of guys that we train. So when you come to UKZN, we give you all the training in terms of chemistry, and then you can now fit into a different type of chemistry application that you would like to do. And these jobs are available all over the world. So quickly, what is chemistry? It is the study of matter and its properties with special attention to the interactions between substances which lead to a chemical change, right? And chemical change may produce new products such as polymers, plastics, cosmetics, medicines, and obviously, produce energy, right? And where is chemistry used? Obviously everywhere, isn't that so? And basically every industry worldwide has chemical applications in one way or another. Were it not for chemical fertilizers, the mass production of staple foods such as wheat, corn, rice will not be possible. And chemistry is needed to study other sciences: botany, zoology, biochemistry, microbiology, pharmacy, engineering, medicine. Almost every other science field requires chemistry. And over 25 elements are essential for human physiology that have been identified. And these are our branches of chemistry. Now, these are what are our main branches of chemistry: analytical chemistry, physical chemistry, inorganic chemistry, and organic chemistry. So analytical chemistry is simply quantitative and qualitative analysis. So what is in a given sample and how much of it is there? So that's what we refer to as quantitative, how much, and what is qualitative by wet methods like titrations is what we call a wet method, and modern instrumental methods like what we have now, atomic absorption spectroscopy. Then we have the chemistry of materials, which is actually inorganic chemistry, right? Where we have a systematic study of the properties of over 100 elements that make up the periodic table. In fact, it's all the elements that come together to make up different types of components. And another interesting part of organic chemistry is catalysis, how we catalyze these reactions to come together. And then organic chemistry, as you know, it's the study of carbon-containing compounds found in plants. For example, extraction of different types of compounds that are anti-cancerous. And organic chemistry plays a useful role in medicinal chemistry, where we're using a lot of plants and we're trying to find antioxidants, anti-cancerous, even anti-COVID components that come from plants, etc. And then chemistry, physical chemistry is basically a study of the physical principles that govern the properties and behavior of chemical systems. So physical chemistry is reaction kinetics, how fast the reaction goes. Okay, so basically this is what looking at. And as you can see, some nice pictures of the different branches of chemistry here. Right, so graduates may choose two streams, that's to venture into industry or to serve at an educational institution while pursuing postgraduate studies. So if you do a degree in chemistry, then you may want to go and work in industry. So you can see on the top right-hand corner, the guy wearing a hard hat, working with complicated systems. Or you may want to, and if you look at below that, or if you look at the left-hand corner, one of our students working in a laboratory, and you can see doing some research. Okay, so graduates are offered many positions ranging from laboratory analysts, research and development chemists, managers of chemical industries and mines, educators at university like ourselves, college, technicon, school, so you can become a chemistry teacher, you can become a chemistry lecturer like myself. So there's so many different ways where you can find yourself as a chemist. And then obviously, as you do postgraduate studies, when you finish a 3-year degree at university, then you can do your honors degree, you can do a master's degree, and you can do a doctoral degree, which is a PhD, and then you can end up working as an academic and as a researcher. Okay, we have other positions at the university. You can work as a laboratory technician. So you can see right on the right-hand bottom, you can see we have a technician. Okay, so you can work as a technician. The university has open days. This I took from another slide, so just pardon the dates, but keep your, I'm sure you may have looked at our open days at the university for this year, and we gave you some access to the information that we have. Right, so let's understand chemistry, and now I'm going to take you through a very nice
extraction of iron.
Okay.
It has been since 5,000 years that man is using iron. Iron is the second most abundant metal in the earth. The most important ores of iron are hematite and magnetite. These ores contain different types of impurities. The first step is to remove the impurities. This is called as concentration of the ore. The iron ore is converted to iron in a blast furnace. This is made of steel in which the inner side is covered using bricks. The mixture of concentrated ore, coke, and limestone are added from the top into the blast furnace. A powerful current of hot air is blown from the bottom simultaneously. During the flow of hot air from bottom to top, coke combines with oxygen in the air to form carbon monoxide. 2C on reaction with O2 forms 2CO. Due to this reaction, a large amount of heat is released, and thus the temperature of blast furnace increases to 2000 degrees Celsius. Carbon monoxide formed in the furnace reduces the ore. Fe2O3 on reaction with 3CO forms 2Fe and 3CO2. At high temperature, calcium carbonate decomposes to form calcium oxide and carbon dioxide. CaCO3 forms CaO and CO2. Then impurity silicon dioxide in the ore reacts with calcium oxide and form calcium silicate, which is known as slag. Flux on reaction with gas forms slag. CaO on reaction with SiO2 forms CaSiO3. The iron obtained directly from blast furnace is called as pig iron. It contains carbon, sulfur, phosphorus, manganese, silicon, etc. in very small quantities. Pig iron is heated to melting and again solidified to get cast iron. In cast iron, 95% is iron. The iron which contains 0.1% to 1.5% of carbon is called steel.
There we go. So you see, when you look at chemistry, it's the chemical equations, and then you're seeing the reactions basically taking place in a blast furnace. So you saw if you took the iron ore, which is basically rock, melting in a blast furnace, and then we get all the steel that we have around us. So in this particular slide, I just want to take you through our labs at UKZN. So if you come and study at UKZN, you basically see our wonderful labs. You can see all the lovely apparatus. So you're very highly trained to basically go through all of the different types of systems, the different apparatus, and the different glassware that you would use, and all the different methodologies and protocols. Okay, you can see the student has a big smile on his face because he's enjoying what he's doing. All right, so in the laboratory, you've got to be very, very observant. You've got to understand what you're doing, and you notice all of our students are very, very well protected in terms of looking at their goggles that they have. You can see their lab coats are nice and white and they clean, and all of them have a good smile. That means research is fun. Enjoy what you do. Okay, so you can see again here, students concentrating, especially when you're working with apparatus that are very, very sophisticated, and you've got to monitor, you've got to observe, you've got to take readings, right? And here are more students carrying out experiments. We have an instrument lab. So in our instrument lab, we have very high quality instruments. As you can see, this particular student has to work with software that is basically driving the instrument next to her. So the instrument next to her, on her right-hand side, that white little box there is called a GCMS, gas chromatography mass spectrometry, okay? And she is now working with a particular instrument, all right? So I'm going to just wrap up with a story about, I call it the Mari biscuit story, right? And this student, as you saw in the previous slide, she used a gas chromatograph, right? If I can play the video. Okay, so basically that's the gas chromatograph that we have here. And now what had happened was, I like eating Mari biscuits. So when I'm watching TV or if I'm studying, I make a cup of tea and I dip my Mari biscuits into the tea, and sometimes it falls and, it gets into your tea and it gets all when you're dunking your Mari biscuits. So one day I went off to Checkers and I bought these Mari biscuits. And when I went back home, I basically got a funny, strange smell from the Mari biscuits. And I said, hey, this Mari biscuit is not smelling right. I got a solvent smell. And then I came back to the lab and I basically crushed the Mari biscuits. We have what we call a sample prep. And then I used another solvent and I extracted whatever was in the Mari biscuit, right? And this here is the actual spectrum of the different components that came out of the Mari biscuit. Can you guys believe that or not? And I was able to identify what these solvents were, which means during the processing of the Mari biscuit, what had happened was there were exhaust fumes and solvents from the process that was getting absorbed into the food that was done. So I sent a report to the manager at Checkers, and he's in turn sent the report to Bakers, the company that did it, and they basically they had to go back and look at the processing, and they did come back and they apologized. And in addition to that, they sent me a huge box of biscuits. And before I sent the report, I said to them, I don't want a box of biscuits, or I don't want to be bribed with freebies. But in any case, I kept the biscuits because they tasted nice and they didn't have a solvent. And so that you can see how we are able as chemists. So you may think that everything is nice and wrapped up very nicely in this packaging, and everything is done. But you see, us as chemists, we have the ability to check whether compounds are suitable to eat and whether they are not contaminated. And this is what I call the Mari biscuit story. And I hope you remember that, and it inspires you that you will not, obviously, from the knowledge that I have and the knowledge that I gained at university and the knowledge that chemistry gave me, I was able to solve this particular problem. Okay. And these were the harmful compounds. We call it the mass spectrometer, and I was able to look at that. And these were some of our students that were training that I showed you earlier on. This is a colleague of mine, Professor Martinchi. She is a physical chemist, and we worked with these students in our laboratory. And there we are in Prague. In 2018, we went to Czechoslovakia. They now call the Czech Republic and Slovakia because they've now separated. Okay, and this was I'm just showing you the medal ceremony of these grade 12 students at Prague in 2018. These are some of our friendly staff that helped us at the labs and that helped the students at the labs. And this was a nice picture that we get to travel. This was Charles Bridge that we looked at Vltava. So good luck in your future studies. Remember, you are already winners by being here, right? You've come to listen to us. You want to be a good trained chemist. You want to be good trained scientist. Give it your best shot, right? And you are going to do well. Think before you give an answer. Keep on searching for a cure, a new compound, simply improving the quality of an existing material, because that's where research starts. Enjoy the learning, writing tests and exams, and may God grant you great strength during, the exams, which I call the competition, which is your exams. Okay. And here is a quiz. I would like to know question 1. So you can, I don't know, organizers, whether the students are able to, or they can just type out the answers, I think, at the bottom there, or they can shout out. Are they able to communicate with us?
Yes, they will
Okay.
raise their hands and then.
All right. So question 1, does anybody know the answer? What is it commonly known as? Delta 9 tetrahydrocannabinol. What is it commonly known as? Anybody knows? Any hands up? Let's see. Any hands up?
Haven't seen any hand.
Not Tishana. Tishana, not you. Vardhan. Okay, let's go. Vardhan Maharaj.
Is it marijuana or cannabis?
Yes, well done. And the street name Zol. Well done. I was hoping you would tell me it's Zol, but it's cannabis, okay? Marijuana. Next one, number 2. What is acetyl salicylic acid commonly known as?
Vardhan, before you continue, Prof. Vardhan, please give me your, I think you gave me your number already, right?
Okay.
What is please type your number in the chat box.
Okay, great. Yeah. Question number 2. What is acetyl salicylic acid commonly known as? You buy it in the pharmacy, you got it at home. We always take it when we have a headache. Acetyl salicylic acid. Come on, I'm sure we'll get a hand raised just now. Okay, Dr. Singh, Tishana, you can tell them.
It's aspirin or dispirin.
Thank you. You need one too, because you were trying to answer the question of Zol. So I think you need some aspirin. Question number 3. You saw it in that video. What is the formula? Oh, okay, Kyle, okay, maybe you're too late. For question 3, were you guys, what is the formula for rust? Controller,
I'm not sure which one was the first hand.
I think it was Kyle. Was it Kyle? Go ahead, Kyle. I think it was you. Oh, and hang on,
Sir,
Akash.
morning, good afternoon, sir.
Afternoon.
I think it's FE 203.
Okay. FE 203. And what does it have attached to it? What does it have attached to it?
Oxygen.
No. You remember we did you see the video?
I did, sir.
Okay, so it's actually Fe3O4 with N waters of hydration. Fe3O4 with N waters of hydration. So it has waters, that means it has water attached to it, okay? But Fe2O3 is acceptable, it's on the right track. I'll give that to you, all right? What is the melting point of sodium chloride? Question number 4, no Googling. Let's see if you can, okay.
Kyle, please send me your number. Kyle, please send me your contact number via the chat box.
I know, Vardhan, you raised your hand again, but can we just give somebody else a chance? I'll come back to you if there's... Okay, there were 2 participants. Who was the other guy?
It's Inati.
Yes, let's go for it.
Is it 801 or 802?
Well
degrees?
done. Well done. How did you know that?
We did it as it was like in our extra notes in our book.
Excellent, excellent. And can you tell me why it's got such a high melting point? I'm really proud of you. Well done.
Oh, I actually don't know that.
Come on, you know it's because of the bonds between Na and Cl. And what type of bonds does Na and Cl have? Because remember, it's sodium chloride, isn't it? Table salt is sodium chloride.
Yes.
So it's basically, what type of bonds do we have in sodium chloride? Ionic or covalent?
We haven't done that yet.
Oh, you haven't done that. Okay, don't worry.
I'm in grade 10.
Oh, you're in grade 10. Well
Yeah.
done. At least you knew something that's in grade 12. Well done to you. Question number 5. Now, I'm assuming
Inati, please give me your number via the chat box.
rather than you seem to know all the answers. Well done to you. But I'm not going to give you another prize. You got 1 prize already. Question number 5. What is the P in pH? Okay. Who raised their hands first? Controller, you got to help me there. Okay.
It's
Who raised their
Pagamani.
hands? Yeah.
Pagamani Kumalo.
Okay. Go, Mr. Kumalo. Fakamani, give us the answer.
Hello. No, I think it's P stand for it's the percentage or percentile of hydrogen.
Good try, but not the right answer. But good try. Well done for trying, and I'm proud of you.
Oh, okay.
The next one? Anybody else?
The next one was Yashoda Governor.
Yashoda?
Okay. Is it potential?
It's not potential, Yashoda, unfortunately. Remember when we do pH, if we say something is pH 7, that means it is acidic, basic, or neutral.
It's neutral.
Right. And what grade are you in? What grade are you in?
I'm in grade 9.
Oh, okay, okay. So you probably, but good. Thank you for trying. It's not potential, but let's see if somebody can get it. I'm really well over time, but the other person there, Mr. Controller?
The Pendulo. The other 2 both won already. So let's go to Pendulum.
Yeah. Let's go to somebody that didn't win.
Yeah. Pendulo.
Pendulo?
It's power.
Power.
Yes.
No, unfortunately, thanks for trying. And I really appreciate the
Presence.
trying. Sorry?
Presence.
Not presence. How? What grade are you in?
I'm in grade 11.
Okay, you should have known that. I think you probably covered it in grade 11. Okay, sorry about that. Next hand. There's nobody there.
Nobody.
Okay. Dr. Singh, do you do what you do best?
I don't know either.
She knows. She knows. She's just lying. It's the minus log of the H plus concentration. Okay. So it's a mathematical calculation on your calculator. If you press log of 7, you will get, if you take log of 1 times 10 to the minus 7 molar, you'll get minus 7, and minus into minus 7 gives you a pH of 7. So P stands for a mathematical calculation of minus log. Okay. So it's minus log. Okay, we'll go to question 6. All right. If you had water and benzene, 2 colorless liquids, which layer would float, and how would you test which is the water layer? This is an easy one. Last question. Oh, we went well over time. This is a nice one.
The nice one, but no hands.
Come on, guys. You have a mixture of water and benzene. I want to know which layer would float, and how would you test which is the water layer? Oh, you can just tell me how you would test for the water layer. Let's see. This you don't even need grade 6, 7, 8. It's very simple. Anybody? Come on. All right. So the answer here is very simple. It works on density. So you know the density of water is 1 at a fixed at 25 degrees Celsius. Because density is temperature dependent, and benzene has a density less than 1. So that means if something is less than 1, it's going to float on top. So benzene is the top layer, but because both are colorless, you're going to simply add a drop of water, and the drop of water will go and dissolve in the water layer. So you'll actually see the drop go past the benzene layer at the top. It also doesn't mix with the benzene layer. And then it'll simply drop to the bottom. So you know that's the water layer. So you see, sometimes, guys, you are looking for really, really sophisticated answers when you don't have to basically get sophisticated answers. All right. You can use very simple understanding of chemistry. So sorry, guys, I took a little bit of extra time, but I hope you enjoyed the talk, and good luck in your studies. Enjoy your holidays, and I will see you in my first year lecture next year in Chemistry 110. Thank you and goodbye.
Thanks, Ajay. Thanks, Tishana. Good to see you, Tishana, after a long time. Yeah, guys, let's see each other tomorrow. Grade 10 in the morning at 9. I think tomorrow we are doing trigonometry. So let's continue tomorrow. Thanks.